Yeah, of course. Thank you. Okay, so we are going to steal 1 minute of a very, very busy program that we have, just to thank you for being here. If you're here, this is FM2, just in case you're in the right room, if you're looking for that. I hope it's a fantastic meeting. The program looks great. I like to, thank the organizers, Eva, my co-organizers, Nami Sakai, who couldn't be here, and of course the SOC. So Mark Kranholz, Mpati Ramatsoku, Margaret Meissner, Yasuo Fukui, Frederick Galliano, and especially Monica Rubio, who is also the president of the supporting division, which is the Interstellar Medium Division. Okay, so I just wanted to say that, and then we can start with the program. What I'd like you to keep in mind is that time is very tight and fully scheduled. So with the questions, be concise. With the responses, be concise. Keep to time. I'm sure our chairs will keep us to time. Thank you.
Okay. So I think I just dive in, right? Great. Okay. In that case, let me flip that around and say thank you very much to the organizers for putting this exciting meeting together. Huge thanks for having me, and I'm super excited to hear the talks and talk to everybody over the next couple of days. I do know that sometimes I talk a little fast. If it is easier for folks to follow along with the slides, I put a QR code and a little URL here that people should feel free to grab that will also sit through the first few slides. But with that, let me dive in. So my assignment was to talk about what new observations tell us about stellar feedback and the interstellar medium structure in nearby galaxies. And I'm going to focus on how we do that from high-resolution multi-wavelength surveys, especially biased, sunk a decade of my life into this, the FANG surveys. So the picture, so the picture that I want you to have throughout the talk looks something like this. So just this cartoon is that the ISM in galaxies, especially the molecular gas, is turbulent, it's highly structured, it's coupled in important ways to the large-scale properties of the galaxy that it resides in. I'll show you some evidence for this. And the thing that, especially through the first part of the talk, I want you to keep in mind is that the ISM is made up of these individual parcels that are evolving through a cycle that looks something like this, evolving from a cold cloud with the onset of star formation emerging over time. And then as massive stars are formed, the newly formed massive stars exert stellar feedback, disrupting and dissipating the cloud around them. And then eventually those massive stars blow up as supernovae, depositing even more energy and momentum into the surrounding interstellar medium, and then clouds reform, and the cycle starts again. And the basic idea behind the FANG surveys is that if you line up the best telescopes in the world to observe the nearest star-forming galaxies at very high resolution, you can break these galaxies into individual evolving regions, essentially catching, space cadet here with 2 clicks, essentially catching each individual part of the galaxy in a distinct evolutionary state. So H2 regions appear in ionized gas tracers, tracing where massive stars have recently formed. Stellar clusters show you where stars have recently formed. ISM clouds visible in CO emissions from ALMA and dust emission from JWST show you the fuel for the next generation of star formation, and so on. And so we've made a lot of progress over the last 10 years covering what are essentially the nearest 75 big southern star-forming galaxies with a combination of ALMA CO, JWST, near and mid-infrared, HST, UV and optical broadband emission, and H-alpha. And it's a new thing to have all of these high-resolution facilities spanning across the spectrum capable of resolving galaxies into their individual constituent parts across the spectrum. I will emphasize, and I won't spend a ton of time describing the surveys beyond this, that all of our data are public and available on the web here, in addition to lists of the too many publications to talk about over the last decade. And I very much encourage you to go check this out, take advantage of the data. The community will do more with it than we can do. There is still much more to do to achieve a complete picture, and just here in South Africa, I want to emphasize the fantastic potential to bring world-class atomic gas and radio continuum data into this picture using MeerKAT, which is an absolutely incredible instrument. But right now, FANGS is a very thorough, high-resolution, multi-wavelength survey that covers sort of 75 nearest star-forming galaxies, but is better thought of as breaking those galaxies into something like 100,000 individual star-forming units, each doing their own thing. And we've learned a lot from these observations and from similar effort by teams like LEGAS and Wisdom. And I'm going to just, in this talk, give you a few highlights. But I'm going to shamelessly plug that I can only do so much in 20 minutes. And if you want more on what we've learned, I want to refer people to this review article that Ava Schinner and I put together that is out on arXiv now and will be published later this year. And delves much more deeply into the stuff that I'm talking about in much more detail and clarity, I hope, than I can give today. But with that said, let me just jump into talking first about what I think observations of stellar feedback are telling us from this kind of data set. And so the big picture here is that for more than a decade, there's been a broad consensus that stellar feedback is critical to drive the turbulence that we see in galaxies, set the low overall efficiency of star formation from molecular gas, and shape the overall ISM structure that we see in galaxies. But stellar feedback is a broad term. So this bundles a lot of things together. And the actual process of stellar feedbacks is complex, it's multi-scale, it's a multi-phenomena problem. And observations are really critical to building our understanding of what this feedback is, what the dominant mechanisms are, and how it affects the interstellar medium. And so what I'm gonna argue here, sort of briefly and at a high level, is that observations of the type that we're getting in FANGS help us constrain the when of stellar feedback, especially the when and how molecular clouds are dispersed, where the feedback, the momentum and energy are actually deposited, especially where supernovae explode and deposit their energy and momentum into the interstellar medium, and what effect the overall feedback has on galaxies. And so the when, I think, is something that people may have seen before, but I think remains a really cool observation, which is one of the neatest things that you can do if you just push to high resolution observations tracing recent star formation and molecular gas showing you the fuel for star formation. What you see is that when you resolve a galaxy into clouds and H2 regions, they're not quite in the same place. They're broadly in the same place. You know, a region of a galaxy is forming stars, but in detail, what you see is that tracers of molecular gas, especially CO emission, and tracers of star formation, especially H alpha emission, will appear in slightly disjoint at high resolution with especially some H2 regions with little or no associated CO emission. So my favorite picture of this from FANGS is on the right, which shows you NGC 628, ALMA CO in blue, and gold tracing VLT Muse-based H alpha emission. And you can really see the offset between these things. It's a really stunning graphical demonstration of this. The current, although maybe not final interpretation here, is that these observations show that stellar feedback rapidly reshapes or disperses the molecular clouds, which are the fuel from which the stars that are now powering the H2 regions have been born. This leaves a significant fraction of young stars still giving off ionizing photons and creating H2 regions without nearby associated CO emission. And so if you model these observations, you can statistically infer a timeline for star formation. If you take the ensemble of a whole bunch of literature surveys, especially I want to highlight work by Jaeyeon Kim, a postdoc at Stanford, and Melanie Chavant, you get a picture like this. So clouds sort of collapse and head towards forming massive stars over something like 4 to 20 mega years, which is another way of saying about a crossing time or a free fall time, back to an old argument made by Bruce Elmgreen, who's here, that star formation proceeds in about a crossing time. And then after massive star formation really sets in, over something like 1 to 6 mega years, the feedback from those massive stars disperses and reshapes the surrounding molecular medium, which can leave you with an association of stars or a cluster or an H2 region without significant associated cold gas, even when it's very young. And it's been of interest, those 1 to 6 mega years are of particular interest because it tells us something important about how this is working. So these plots, which are a little bit complicated, but the main thing here is these plots show you the output of a young stellar population that's formed at a particular time. They show you the ionizing photon, bolometric luminosity, wind power output of a young stellar population over time after it's formed. And what they show you is that, or the critical thing here, is that if you look at the purple, that's showing you where the supernova explosions, which create a ton of energy and deposit a ton of momentum into the ISM, will go off and deposit energy in. And if you compare that to the shaded region, essentially the dispersal and reshaping of the molecular medium by stellar feedback is occurring before most of the supernova will go off. And if you believe that the most massive stars don't go supernova, which is the thing that if you talk to supernova people, they believe right now, then this gets even worse. And so the first supernova will be going off after statistically the molecular ISM has been substantially reshaped by stellar feedback. So Supernova aren't doing it. This has led to a lot of attention on pre-supernova feedback as a major factor in the evolution of molecular clouds. What can do it? Well, certainly radiation pressure and stellar winds are important. After you've heated the gas up, the thermal pressure of the gas can be important, photoionization can be important, and cosmic rays may play a big but underappreciated effect. And I think there's going to be significantly more discussion of the theory of this in Steffi and Rowan's talks, in Steffi's talk. Rowan's shaking her head. So, but from the observational side, there's been interest in digging into what actually is happening here by making observations of regions after stars have formed and attempting to infer the strength of these individual feedback mechanisms. And from the observational point of view, the thing that I want to emphasize is that this is hard because you essentially need to resolve individual star-forming regions. The basic geometry that you're thinking about is a shell getting pushed on so that it's something like L over 4 pi r squared. And that means you need to resolve individual H2 regions, which in the Milky Way are something like 5 to 10 parsecs across. That's tough, and it's been really tough to do from the ground, except in the absolute nearest galaxy. So a lot of the literature here has been previously based in the Milky Way, the Magellanic Clouds, the local group. But with HST and JWST coming online, a very exciting thing now is that the prospect to actually assess the strength of individual pre-supernova feedback mechanisms, radiation, stellar wind power, things like that, is coming into focus for galaxies out to something like 15 to 20 megaparsecs. And so this is, I'm going to say this is fun because it's fodder to discuss at the conference, although I wish I had a punchline for you. I think in a year, we're going to have an incredibly sharpened view of the effect of individual stellar feedback mechanisms on tens of thousands of H2 regions. As new HST-based sizes, and I want to especially highlight new contributions from Ashley Barnes at ESO and Rupali Chandar at Toledo. The strength of radiation pressure, which Deb Patak, I think is here, will give a talk on later today, and you should talk to Deb about stellar feedback and especially radiation pressure. And a variety of other observations that I'm not going to sort of rattle off for you here, all come together to give us a view of the strength of the individual feedback mechanisms in regions across the local galaxy population. But in order to not leave you without a punchline on this particular point, what I want to say is that from the observations of the very nearest galaxies, we do have a sort of idea right now, which is that at very small scales and early times associated with individual star-forming regions, so say less than a parsec and significantly less than a megayear, the stellar winds and the radiation play a very important role. And then as the regions get bigger and more evolved, the heated gas, the NKT, I have a 10,000 degree gas pushing outwards in the region takes over, and the thermal pressure associated with the H2 regions drives the long-term expansion over the later times. So I think this is what I would say on the pre-supernova feedback mechanisms, but I feel like the appreciation of pre-supernova feedback's importance has slightly led us to forget the fact that those supernova are now free of their molecular clouds, and they are giant nuclear bombs that are going to go off in the interstellar medium. And so there's a complementary part of this that I think is very exciting and has some very interesting interfaces with numerical simulations, which is that with pre-supernova feedback reshaping molecular clouds, now the supernova, which deposit 10 to the 51 ergs of energy and huge amounts of momentum into the interstellar medium, are free to go off somewhere. And at least for us, this is the simulation. And I think Steffi will give a talk that will talk about this later in the week, tomorrow, I think. But for us, this is the simulation picture that launched a whole raft of observational tests. And what this basically shows is that in the Silk numerical simulations, where you put your supernovae, whether they go off in low density gas or high density gas, has a very strong effect on both the zone of influence of the supernova and the ultimate shape of the interstellar medium that you're looking at. So if you randomly distribute your supernova, you get a very different looking interstellar medium than if you put the supernova directly at density peaks. And the cool thing is that people have been surveying the local galaxy population to write down where supernovae go off for decades, really centuries. You can go back and find one in M31 in the late 1800s. Astrometry, not that good. But we have these maps of the interstellar medium, and we have the recorded locations of supernovae, which have not yet dramatically processed their surrounding media And so there's an ability to measure the location at which supernovae explode into and deposit their energy and momentum. And Nestmaker Chen did a very fun PhD thesis on this, and you can see examples of this here with supernovae distributed in the Fangs-Alma CO map, showing you molecular gas on the left, and H-alpha map in nearby galaxy NGC 4303. Keeping with the sort of high level, I'm going to cut to the chase on what you find, which is that at sort of 50 to 150 parsec resolution, you get something like 40% of core collapse supernova appearing associated with an H2 region or a molecular cloud. So that's already a lot of core collapse supernovae that are not hanging out in dense peaks and are free to blow up in the low density atomic phase of the interstellar medium and have a very wide zone of impact. This becomes an even stronger statement when you start running controls and you say you would expect 30% coincidence already by chance. And so now you're talking about an excess, and the punchline here would be that statistically, we think there's an excess of something like 10 to 20% of core collapse supernovae that are associated with H2 regions. And overwhelmingly, these are the 1BCs, which are massive, the most massive star supernovae, stripped envelope things. And so this is highly consistent with pre-clearing before supernovae go off, the picture that I was telling you about a couple of slides ago. But it also gives a very quantitative statement if you were running numerical simulations that track individual supernovae, which is hard, but is done at this point, and want to compare. There are limitations here. Supernovae are maddeningly rare in terms of when they actually explode. This is probably good for us, but it's bad for doing this project. We are limited by the resolution of the CO and H-alpha and the astrometry for the supernovae. So all of that will get better. But I think there's a very clever way around it that I want to highlight for a moment, which is that you don't have to only do this project with individual supernovae. We know which stars are about to blow up as supernovae. And there are a lot more red supergiants than there are actual recorded historical supernovae. So highlighting work by Sumit Sarbadakari here, working in the local group in M33, where you can get a very high physical resolution map of the atomic gas and place the red supergiants, which are core collapse supernova progenitors, and the Wolf-Rayet stars, which are likely to be high mass supernova progenitors, into not just molecular gas maps or H-alpha maps, but into actual atomic gas maps, which traces most of the interstellar medium in galaxies. And what you find is that the red supergiants are distributed almost statistically indistinguishably from the atomic gas at large in M33. So they're really going off. We really expect the core collapse supernova to go off in low density parts of the interstellar medium. And this is great if you want to stir turbulence and support a galaxy disk. The Wolf-Rayet stars are significantly more concentrated towards molecular gas peaks, which is something that people have observed in other ways over the years. And I think this is just a shout out to talk later tomorrow, I think. Nick's nodding. So I think the ability to do this in high physical resolution atomic gas maps is really exciting. So I want to call attention to what we'll hear from Naomi and Nick on very high physical resolution mapping of the local group galaxies in the 21 centimeter line. This is, I think, this is result of VLA program, recent paper by Nick, obtaining the first sub 20 parsec resolution 21 centimeter maps of any galaxy beyond the Magellanic Cloud. So I'm very excited here by the work that Nick's going to tell us about. And I think there's a prospect to place a lot more of these future supernovae into atomic ISM context. So pushing ahead here, I'm going to say a couple words very briefly on what effect. If you zoom out even more, I want to point out that comparing the rate of star formation that we observe in galaxies to the weight of the gas that must be supported by stellar feedback also gives us a very good handle on the net effect of stellar feedback in galaxies. And so the idea here is that if you calculate the weight of the interstellar medium in the galaxy's potential, we think that stellar feedback is essentially supplying the momentum that is actually holding that weight up in a galaxy that's self-regulated by star formation. And so this is something that you can do if you don't need a 50 parsec observation of galaxies, but even with kiloparsec resolution observations of galaxies, you can compare the weight of the gas, compare that to the rate at which stars are forming. And that tells you about the momentum that is deposited per unit stars formed into the gas disk in order to hold that gas disk up. So there's been a bunch of recent work on this that I think is exciting that have led us to a good assessment of the sort of net momentum per unit stars formed that are injected to the ISM on large scales. So this is showing you work by Jai Sun in the FANG sample of galaxies. There's also been work in the EDGE sample of galaxies, and Deanne has worked on this for the Dynamo sample of galaxies. But I think this is something that mapping out the environmental variations of this, comparing this to numerical simulations, not just of individual patches of galaxies, but big samples of galaxies as a way to test whether observations and sims are telling us the same thing, I think has a lot to tell us over the next few years. And I think this is a very exciting direction. So I want to highlight that. If you want one number, it's 1,500 kilometers a second is the specific momentum yield of stellar feedback in local galaxies. I don't know if anybody was waiting for that number. I don't think so. I will just say 2 words on what I won't talk about, but that is also coming up here at the meeting. So obviously when feedback gets away from you and you're not in an equilibrium situation, galactic winds can be launched. This is very important to chemical evolution, to quenching. Dan is going to talk to us about this later in the week. And one of the most striking things we've seen in pictures of galaxies over the last few years has been these giant bubbles carved by stellar feedback. There's a lot to say here. There's only a limited amount of time. I'm already going to get myself in trouble over the next 3 minutes, I'm aware. But I refer you to, Karina Barbosa has a poster on this asking, do we see X-rays inside this stuff? And you should track down Karina and talk to her about this over this week. I'm going to just say 2 fast words over a few slides. I know, which is just, so overwhelmingly, I wanted to talk to you about stellar feedback. This is just sort of 3 slides here that I want you to internalize on ISM structure. This is overwhelmingly published, so it's mostly referring you to published work. But I will say, with a major investment by ALMA, we have really mapped out the structure of the molecular interstellar medium in galaxies at 50 to 150 parsec scales over the last decade. And what I want to highlight here is that if you look at the surface density and line width of galaxies, as you go from galaxy to galaxy and environment to environment, they just look different. And then these are cartoons. These are plots that I expect you to internalize as a sort of flashing by, not to read in detail. But if you take the ensemble of work by studying mergers, especially by Chris Wilson's group, the studying early types, especially by the Wisdom group, and the FANG's observations of star-forming galaxies, what you see is that the sort of 100 parsec resolution, line width, and surface density of molecular gas and galaxies both shows significant range within any individual environment and varies as you move between these distinct dynamical environments. And I think what's even more exciting than just seeing differences between dynamical environments is that there are very regular scaling relations. So that if I told you the large scale structure of the disk that you were hanging out in, so the large scale stellar surface density or the large scale star formation surface density at a sort of kiloparsec resolution, you have the ability to predict the mean cloud scale properties of the gas in that individual patch of a galaxy. So giant molecular cloud populations show a coupling to their disk and to the local disk, and they obey very regular scaling relations here. This is last one, and then because Karen will cover the last bit. So what I'll say, just as a note here, is that for the experts, the spectroscopic observations, things like HCN observations and N2H+ observations, are giving us a very consistent picture here with what we're seeing with the CO imaging. I think that's been very exciting. You take a look at the slides, I'll highlight papers by Sophia Stuber and Lucas Neumann. We're seeing a very consistent picture where these line ratios tracing density and the physical state of the gas show similar environmental variations to what we see with CO imaging. And I think with that, in danger of getting chased off the stage here, I'll just end with the future here is dust, at least in the immediate term. Dust, it gives us dust from JWST, gives us very high resolution, high sensitivity maps that are also ISM maps. And so Karen will talk more about this as an exciting path forward for pushing on ISM structure in the local galaxy population. And with that, I will say thank you and beg the chair's forgiveness for going a couple slides over.
Thank you very much, Francisco.
I'll answer very quickly, I promise.
I was already enough for
Mhm.
I want to ask about mechanisms.
Uh-huh.
Like, do you have organized mechanisms?
Yep.
Dynamic mechanisms?
Yeah, so that's right. So there is, this is too hard of a question to answer very, very quickly. I will say, when I'm showing you a lot of these CO results, we haven't we've worked very hard on metallicity dependence of the CO to H2 conversion factor. Karen, and I think Eltha will mainly talk about emissivity variations, but Karen and Eltha will talk about what we know about the CO to H2 conversion factor, which shows a very strong dependence on metallicity. The balance between atomic and molecular gas, I think Barbara will talk about, shows important dependences on this. So the metallicity super matters. It's correlated very much with potential well and galaxy mass. And it does enter the analyses here, but that's sort of, it is a good question is all I can say without getting in big trouble.
Thank you. Yes, we have time for one more question. Really? Yes, go ahead.
Environment. And so you had this little timeline about the star formation traces, the molecular component. If you have an environmental trigger, say gas compression, do you expect that those tracer time to be different?
Yeah, so there's a bunch of, I mean, the next talk, well, so you hear me being in a cluster or something like this.
Oh, even just a tidal interaction, like you could have a pair
sure.
that doesn't make it.
I mean, so Nikki's going to talk next about the effect of environment on these things. So I think that there is a big effort. I'm going to, again, shamelessly plug Jason's work to observe an almost parallel set of observations for Virgo cluster galaxies. So arc second CO observations building on the Vertigo and MAUV observations. So this is coming. I think the answer is yes. You have additional sources of pressure, but in particular, I've shown you a lot of things that are about what happens once the molecular gas forms. If I had to put money down, the most important thing is going to be compressing the gas to turn the atomic gas molecular and then stripping away. I mean, that's something that's been observed for decades, stripping away the atomic gas. So I think the dominant thing will be in the molecule formation.
Thank you very much. I think we have to move on. So thank you very much, Anna. And the next talk is by Nikki Savel, right? Savel from UCT. And while Nikki is setting up, I'd like to take a second. I'm introducing myself. Go ahead. Yes, go ahead. You should have your talk ready. My name is Ezekiel Treister. I will be chairing the first session. I know we started kind of in a hurry, but and it's a very packed program, so.
Awesome. Thank you very much. Thank you for the introduction and for having me here and for the nice little bridge from the previous talk to mine. I'm all pumped up for the previous talk, so hopefully I'll manage to stick to the time. So today I would like to talk to you a little bit about a hopefully mostly coherent view of the molecular and atomic gas in nearby galaxy clusters. And I would like to mainly focus on some recent results in the Virgo cluster, but I'll also briefly touch upon the Fornax cluster and some other nearby clusters as well. This thing looks very complicated, so let me see if I find the right button. Yes, I found it. Okay, so before we get started, I would like to highlight some of the most important differences actually between the molecular and atomic gas when it comes to observing these gas phases in dense environments. So in dense environments, a lot of environmental processing happens. I'm showing a few of these processes here in these very cute little cartoons. I don't have time to explain all of them in detail, so hopefully you're at least vaguely familiar with most of them, but do feel free to interrupt me if I don't make sense. So the atomic gas is typically distributed in large extended disks, is relatively loosely bound to the galaxy, so it's relatively easily removed from galaxies by all these environmental processes that are happening. So as such, atomic gas has been used as a tracer for environmental processes very successfully for a very long time. So that is very nice. The molecular gas, on the other hand, is a lot more tightly bound to the galaxy. It's a lot more centrally located. So it's not as obvious what happens to it when it's processed by the same environmental processes as the atomic gas. So it's only a bit more recently that we are seeing that molecular gas can also be directly affected by the same processes. So this is, you can see this quite well in this little image here. This is a galaxy that is in the Virgo cluster, which has been studied by the in the atomic gas that you see here in red. And it's very clearly being ram pressure stripped. And then in the blue contours here, you can see, oh, my pointer just broke, the molecular gas, and you can see that it is a lot more compact. You can imagine that it's a lot more difficult to strip away from galaxies in the same manner. So I'd like to start by mentioning some results from the recent Vertigo survey, which is the Virgo environment traced in CO survey, which is based on the earlier VLA imaging of atomic gas in Virgo spirals, the VIVA survey. So you can see the Virgo cluster here with the atomic gas images from VIVA on the left, and similarly the molecular gas images here on the right. So these are magnified by a factor 10, these by a factor 20, so you can immediately see again sort of what is the scale and the size difference between both different gas disks. And what I was personally interested in, so the project I led within the Vertigo framework, is to see if the environmental processes that we have identified now, oops, wrong button, with the VIVA survey, if they reflect also in the molecular gas observations from Vertigo. So we can start by looking at sort of the total gas content, so the total atomic gas content and total molecular gas content of these galaxies. So we can define something that is the H1 deficiency, which is basically we know how much H1 we expect in a galaxy based on other properties such as optical size or mass or something like that. And if a galaxy in a dense environment deviates from that relationship, if it's much lower than a scaling relation, we can measure the distance is basically the H1 deficiency. You can define something similar for the molecular gas deficiency in a little bit of a different way. And basically here I'm seeing whether the H1 deficiency here on the x-axis can predict also the molecular gas deficiency in Virgo galaxies here on the y-axis. So we can ignore these classes for now, don't have time to explain them. But what we can see here is basically that galaxies that are deficient in H1 are also to some extent deficient in H2. So most galaxies in Virgo are here in the upper right quadrant, which means that they are gas poor in both gas phases, both atomic and molecular gas. But we can also see that whereas the H1 deficiencies are quite serious, there's galaxies with 10 times as little or even 100 times as little H1 as we would expect. The molecular gas deficiencies are a little milder. So they are a little bit deficient in molecular gas, but not quite as serious as the atomic gas, which is maybe something we would expect based on what I just said earlier. The other thing that is interesting to highlight is that these galaxies up here, the green numbers, those are very well-known studies of ram pressure stripped galaxies. They are very well-known galaxies that are being very actively processed by ram pressure stripping. And we can see here that these galaxies actually have, relatively speaking, a lot of molecular gas compared to other galaxies in Virgo. So that is also something interesting to keep in mind. Now, of course, the nice thing about these ALMA observations of the molecular gas in Virgo galaxies is that we have resolved observation as well. So we can study in a bit more detail what exactly is happening with this molecular gas in galaxies that are that we know are being processed by environment based on their atomic gas. So what I've done here is I divided the Vertigo sample into 3 categories. So the galaxies that are relatively H1 rich, they have a lot of H1 or they are just a little bit H1 deficient. Then the galaxies that are a little bit H1 deficient and the galaxies that are very H1 deficient. And I'm showing here their molecular gas radial profiles and also comparing them to the Heracles field sample to have an idea of what they're doing compared to the field. So what we can see here really nicely is that the galaxies that are very deficient in H1 in Virgo, they have much steeper and much more truncated radial profiles compared to galaxies that are very rich in H1 in the Virgo cluster. So this shows you basically that, they are processed by the environment. They lose a little bit of molecular gas, but the reason they have not lost so much molecular gas mass yet is that the gas that is being stripped is very much an outside-in stripping of the lower surface density molecular gas. And this is something that is also found by Ian Roberts et al. That also explains a little bit of this. So one thing he's done is he's looked into the difference between the leading and trailing sides of galaxies that are being ram pressure stripped. And he actually finds some evidence that on the leading side of ram pressure stripped galaxies, where the ISM is a little bit compressed, there's actually an enhancement in the molecular gas content. So actually we get a little bit of an enhancement of molecular gas there. And Toby Brown, who led the Vertigo survey in his more recent paper, has sort of tried and put all these results together. And he's basically found a more comprehensive story of, okay, ram pressure first compresses the gas and enhances the molecular gas content and enhances the star formation. And only after that does it remove the molecular gas from the system and actually quenches these systems. So this is all very nice results from Virgo so far, but we also have to keep in mind that both the Vertigo and the Viva surveys are targeted surveys. They have selected gas-rich, massive spiral galaxies, mostly 50 of those galaxies. And we are still missing out on quite a large fraction of the galaxy population in Virgo. So we're now in the process of changing this with the Meerkat Virgo cluster survey. So this is now scanning basically with Meerkat the continuum and the H1 in Virgo out to the virial radius with the same footprint as these previous surveys. This is going to submit it probably in the next couple of weeks. And here you can see already one result from these from the paper, the survey paper that will be submitted soon. So this is a galaxy that was previously in the Viva survey. So that's the dashed black contours here. And we can now see this very nice stripped gas tail in a lot more detail as well. We're also working on molecular gas observations of some of the new H1 detections. So there's already been a bunch of new H1 detections of more fainter galaxies and dwarf galaxies and galaxies that were not targeted in H1 before. And we've already have some very nice JCMT detections of the molecular gas in these galaxies. And we're working on getting some more of that as well. Okay, so that's all for Virgo. Now I wanted to touch briefly upon the Fornax survey. So this is a very nice result from Alessandro Loni. And what we can see here is again, sort of the same picture. So what he's done, he's looked at the molecular gas mass over atomic gas mass ratio in the Fornax cluster. And here we are sort of again seeing the same thing where most galaxies in Fornax have enhanced molecular to atomic gas ratio. So we can see again that most of the atomic gas will be stripped before most of the molecular gas is stripped. Although from these ALMA observations, again, we can see very clearly that the molecular gas is being affected, it is being disturbed by environment, but it's not removed at the same rates as H1 just yet. And so I wanted to again highlight what we can do now again with Meerkat. So I'm touching briefly upon the Meerkat Fornax cluster survey. Filippo will talk about this in detail around this time next week. So the galaxies that I'm highlighting here now in red, those are galaxies that with the ATCA survey that from the previous slide, they are basically upper limits in H1. And now that we've been scanning the Fornax cluster with Meerkat, with a lot deeper, a lot more detailed observations, actually a lot of these galaxies that were previously upper limits, we can now detect. And a lot of these galaxies that we are detecting now that we previously didn't see are actually dwarf galaxies. So Dane Kleiner published a nice paper about the H1 content in all these Fornax galaxies last year. I'm currently working on a detailed study of a couple of these dwarf galaxies over here, both in atomic gas, molecular gas, and ionized gas as well. So yeah, so previously we didn't see them, and now we're actually resolving the H1 in these galaxies in a lot of detail. So just to give you an idea of what more we can do now with Meerkat. Another very nice recent result is this paper that came out this year by Paolo Serra, who has studied the gas in this dwarf galaxy NGC 1427A, which has been studied in a lot of detail in the past as well. And now we're able to really model and study this galaxy in a lot more detail to try and see what is going on in terms of environmental processing. Okay, so to conclude, I just wanted to give a very brief overview of similar studies that are going on in other nearby clusters. So this is just an overview of all the studies that are happening or have happened in the recent past of people studying the combination of atomic and molecular gas in nearby clusters. You can see a lot of it is already being done with Meerkat as well. So there's a lot of exciting progress being made in this field. And hopefully I've been able to demonstrate a little bit how much more we will be able to do still now that Meerkat is online and in the future as well with SKA. So this is a nice figure kindly provided by Filippo as well, where we can see a few of the surveys that I just mentioned. So for those who are familiar, the Meerkat Fornax survey, the Victoria survey that I just mentioned, and Mongoose as well. And this is just to give you an idea of how efficiently the SKA will be able to do similar kinds of studies, and with more time, we will be able to go much deeper still. So that's all from my side. Thank you very much.
Thank you very much. Questions?
Very nice talk. We had also found a lot of H2 in the run pressure tails, there were more H2 than H1. So I don't know if you find that also in Virgo, because it was in Coma and Norma with Pavel Rashim and collaborators. So do you find also ramp pressure tail in Virgo, or maybe Virgo is a less dense cluster that you don't find more molecular gas in the ramp pressure strip tail?
Yeah, I'm not actually sure if we have seen in that much detail. There's actually molecular gas in the tails themselves. I don't know if we can see that so clearly in Virgo. Yeah.
Other question? Yes.
In your figure, when you're showing the molecular radial profile as functional H1 deficiency, it looks at the most H1 deficient galaxies, they have actually higher cell surface density in the center than the intermediate class. Do you think that is just a sample fluctuation, or it reflects some real physical condition, like the different galaxy types or different localized environment?
So you mean, sorry,
Yeah, I mean, the
You mean
purple curve is
the purple,
higher,
yeah.
higher than the pink.
Yeah, so they are, as you say, they are not huge samples, so I wouldn't read too much into this small difference, but they are kind of similar in the center. So it could be that just the stuff in the outskirts is being stripped and in the center it's kind of the same, but it could also be that we see some of this effect that ramp pressure strip galaxies are kind of have gas compression in the center, and we see a little bit of enhancement, but I don't really want to jump to conclusions just based on that. Yeah.
Maybe one quick question, if it's quick. Please. No, no.
Not having to yell. I will not yell. Is there much molecular spectroscopy beyond CO, say looking at whether the HCN to CO is enhanced or the 13CO to 12CO ratio changes, indicating changes in the physical conditions in the molecular gas?
Yeah, I think some people have been working on some Virgo projects or vertical projects doing that, but I don't know from the top of my head what are the results, but people are definitely working on that, yeah.
Excellent. Thank you very much, Miguel.
Thank you.
And our next speaker is Barbara Cantinella.
Okay, thanks.
We need to wait. Please.
Good morning, everybody, and it's a pleasure to have a chance to talk today. I'm waiting for my slides to be there, I guess.
Yes. Just a second. They're coming.
Okay, thank you. So I guess I'll advance like that. Okay, perfect. Okay, so hello, everybody. I'm going to talk again about environmental effects on the coal gas content of galaxies. So Nikki gave a great introduction to my talk. Thanks for that. And I will focus in particular on some scaling relations, and in particular what happens to the gas that is left in these disks in Virgo galaxies after lots of their H1 gas was stripped. So you already heard about environmental effects, of course, and in particular, as Nikki showed very clearly, we know that H1 is removed from galaxies in high-density clusters, environments like Virgo, but also H2 is affected, but to a less extent than the H1. And I'm also going to use the vertical survey, which you already heard about, a large ALMA program led by Toby Brown, to see what happens to these inner reservoirs of galaxies, of coal gas in these galaxies. And I'm going to just to point out about vertical that our spatial resolution is about 1 kiloparsec. So I'm going to combine maps of coal gas, both H1 and H2, and also stellar mass maps to look into what happens to these coal gas reservoirs. Starting with some resolved scaling relations, we can see here relations between the H1 surface density on the left and H2 surface density on the right, plotted versus stellar mass surface density. And here the vertical points, the vertical contours are shown in red and compared to a control sample that is extracted from Heracles and Fink surveys that is matched to vertical in stellar mass and inclination. And so you can see what we already expect, that when we are in a dense environment, both H1 and H2 surface density are suppressed compared to the control. More interesting, but this doesn't tell us too much yet, so it's more revealing to look at individual galaxies. So I picked a couple of galaxies here, one on the left that is H1 normal, and one on the right that is H1 deficient. And you can see on the top the H1 surface density plotted versus stellar surface density, and on the bottom the molecular surface density. So basically on the left side on a H1 normal galaxy, we see that the data points that are in blue are consistent with the averages from our control sample, so nothing much happening here. When we move to an H1 deficient galaxy, what we see is that the H1 and H2 are suppressed compared to our control. And notice that here I'm talking about the H1 that is left over after the main stripping event. So the H1 density of the gas that is left there is diminished even within the the H1 disk. And also for the H2, we see suppression, we see clear truncation effect. You can also see that, as expected, the radius to which we truncate the H1 moves towards the inner part of the galaxy when we move to a strongly H1 deficient galaxy. So this is just two galaxies to give an example of the trends. If we want to have a more statistical view, we can look at the distribution functions of the H1 and H2 surface densities. So you can see here the results. Well, I beamed the sample, divided the sample in two. On the top, we have galaxies that have moderate H1 loss, and we have galaxies that are strongly H1 deficient on the bottom. And you can see the density distribution of H1 on the left and H2 on the right, compared to the control sample in gray. So we can see that in every case, there is a displacement towards lower densities for both H1 and H2, and this displacement, of course, is much stronger when the galaxies are more H1 deficient. And we can see that, as Nikki already mentioned, typically the effect is much stronger for the H1 than the H2. So one interesting question looking at all this plot is why the molecular gas is suppressed. So there are basically two possibilities, two broad possibilities. One, that also H2 is directly removed from the disk. Or maybe since we remove the H1, that leads to a maybe less efficient formation of H2. And so we end up with less H2 for a reason that is not due to direct stripping, just related to H1 to H2 formation. So in order to test this, we came up with a simple toy model. So basically, which is shown here. So basically, we are looking for clues looking at the H2 over H1 surface density ratios. And in this plot, I show galaxies that are sorted by increasing H1 efficiency from left to right. And basically, what I'm doing here is to compute in the H1 to H2 ratio. The points are our observations, but then we are trying to predict what is the molecular to H1 ratio that we expect when this ratio is regulated by mid-plane pressure, for which we have a proxy here. Since we don't measure the pressure, we just have this combination of stellar surface density and total gas density, or if it's regulated by fixed total gas density on the bottom. And so basically, we have the control here shown in gray as usual. And so what we mimic is what happens when we have only H1 removal. If there is only H1 removal, then we end up with these red lines. And so, and then we compare this expectation for the two cases with our points. And what we see is that for galaxies that are not very H1 deficient, the points line up pretty well with the red lines, meaning that we explain what we see basically just with the H1 removal. No need to affect the H2 gas. When we move to more H1 deficient systems, this is no longer the case. So as you can see, the situation is complex. There are differences between different galaxies, but at least in some cases, the points are clearly between the control sample and what we expect from just H1 removal, meaning that in some cases, we need to invoke direct stripping of H2 from the disk to explain the points. So this will suppress the molecular to H1 ratio, explaining our observations. Okay, so this is an interesting clue of what happens, and in particular at the IH1 deficiency, our observation suggests that H2 is removed as well. So how does this affect the relation between molecular gas and star formation? In particular, does this affect the efficiency of star formation? And we can, and I looked at this in this slide. So on the left-hand side, I'm showing the results for our vertical galaxies being according to the H1 deficiency. So basically, you see the H1 normal galaxies in blue and the H1 deficiency in red. And this is a plot of star formation rate surface density versus molecular gas surface density. So lines here show lines of constant depletion time. So you can see that when we look at the H1 deficient galaxies, the depletion, molecular gas depletion times increase slightly. So this might be due to environment, but we have to be careful that this is not the only explanation. So if we look at a sample of galaxies that is representative of the local galaxy population, so there is no environment here. So these are results from the X-gas and X-core gas surveys. And this plot is a bit complex, but basically what I show here is that the main sequence galaxies are on this gray line, and these lines show what happens when we move away from the main sequence towards gas-poor systems. So when we do this, the H1, H2 content decreases systematically, but there is also a change in star formation efficiency, which is the inverse of depletion time. So basically, when we move towards gas-poor systems, the depletion times get longer. And this has nothing to do maybe with the environment, because this is not a sample that is representative for high density environment. So whatever is the reason for these increased depletion times in these galaxies, what we need to have better data to understand actually what's driving these. And so in the last couple of minutes that I hopefully have, I'm going to show highlights from a survey that we are carrying out to answer these, to look into these effects in more detail. So this is the MOVE survey. MOVE stands for Muse and Alma Valley in the Virgo environment. And this is a large ESO Muse program targeting 40 galaxies in the Virgo cluster, pretty much building up on the Virgo survey that I just talked about. And so for these galaxies, we know the info stages, and we have resolved H1 and CO maps. We are getting high resolution H1 and CO data with follow-up programs. And basically, with Muse, we are getting information about the stellar and ionized gas components of these galaxies at 100 parsec scale and across the entire H2 disk. So you can see here an example. This is one of these our targets, where you can see the optical image. The contours are the CO data from vertical, and the squares are our Muse mosaic to study what's going on in these galaxies. So you can think of this survey basically as FANGs in the Virgo cluster. And so one of the questions that we want to answer is what happens to these reservoirs that are left in gas reservoirs that are left in these galaxies, and how star formation quenches in this galaxy. Because as I said, the depletion times are long, so it's unclear how star formation will stop in these systems. And one possibility are outflows. And so I wanted to show this slide. With the MOVE, we are finding example of outflows, not only in star-forming gas-rich galaxies, like this example here on the left. This is work led by Adam Watts, published early this year. So this is a galaxy that is located about a dex above the star-forming main sequence. So beautiful bipolar outflow, maybe not surprising. But we're also finding cases like this one, where we have a very gas-stripped galaxies with not much gas left in the center, but still there is here a star formation-driven outflow in this leftover gas. And this is a galaxy that is located one dex below the star-forming main sequence. And so this is an example of, this is a possible explanation of how star formation can quench in these systems that are gas-poor, but not completely devoid of gas, where star formation can actually proceed for a giga-year or more. So these are my take-home messages. Quickly, we have evidence of environmental stripping of H1 and H2. Interestingly enough, also the H1 within the disk is affected by these environmental effects. So environment is not just about stripping the outer H1, but also lowers the H1 density in the gas that is left. H2 is affected, but less than the H1. And we have evidence for longer depletion times in this remaining molecular gas. And we survey with the MOVE, we'll be able to understand how star formation quenches in this system. And the way forward that I find especially exciting for me is doing a survey at 100 parsec scale for large MOVE-like samples with H1. Thank you.
We have time for one quick question, hopefully.
Thank you. Given the short lifetime of H2 clouds, less than 10 megayears, is it really possible to separate the H2 stripping from the H1? Because any cloud that you observe is likely to be a kind of second generation that's formed subsequently after the stripping event.
Yes, so of course we are looking at much larger scale than individual clouds, so things get averaged out. Even, well, for the vertical galaxy that I talk, it's 1 kiloparsec resolution. So I guess these things gets averaged out. Maybe we can talk a bit more offline.
Okay. Okay, but hopefully very quick.
Regarding the outflow,
yeah,
you have seen very spectacular evidence from H alpha, which however may not bring out a lot of mass. So do you also have any sign of evidence in the cold gas phases, H1 or H2?
Yes, so we are getting actually much better data with Meerkat of some of these galaxies without flows to answer exactly that question. So there are hints from less resolved data, but of course we need more spatial resolution to get anything meaningful.
Okay. Okay, thank you very much, Barbara, for a fantastic talk. And our next speaker is Petro Jansen. Okay, go ahead, from SAO.
Good morning, everyone. My name is Pietri Janse van Rensburg. I'm a PhD student at the South African Astronomical Observatory and the University of Cape Town. And I will be presenting some of the work that we've been doing for my PhD titled Studying Gas Flows in Nearby Sunburst, Starburst Galaxies and Lurks. I will also briefly introduce some of the work that's been done for my supervisor, Dr. Moses Mkhotsi. So let me first introduce you to the sample. We have been looking at galaxies that form part of the Sunbird survey. The Sunbird survey contains more than 40 starburst galaxies and lurks, but our focus has been on a subsample based on the availability of lower and higher resolution data. In this subsample, it contains starburst galaxies and lurks, like I've mentioned. They are nearby and they cover a wide range of interaction stages. So when we look at the BBT diagram and the color plot using wise colors, we can see again that they are mainly starburst galaxies and lurks, and the majority of them are driven by star formation, but there are also a few in the composite region, and at least one that I know of with a weak AGN. So how are we studying these gas flows, and how are we continuously still planning on studying these gas flows? So the majority of the work has been done using long-slit spectroscopy from the Southern African Large Telescope located in Sutherland. Using this, we could then trace the ionized gas with H alpha, like we just saw in the previous talk, but also the neutral gas can be traced using optical data using the sodium D absorption lines. And in addition to that, we also looked at the stellar continuum in order to compare all of the gas flows with the stars. In addition to that, some of these galaxies does have ALMA data already available, so we could also look at the molecular gas. In the future, very near future, We have also applied for radio data from NEARCAT for some of these Sunbird galaxies. And in addition to that, some of the Sunbird collaborators does have JWST data available for the Sunbird galaxies. And very excitingly, recently there's been a SALT optical and near-infrared IFU has been installed on the telescope, and we have already started getting data for one of the galaxies from the near-infrared IFU. So more to come on these galaxies. So just briefly showing what the data looks like. So we have data along the major and minor axis for most of these galaxies in two different ratings. The first rating is called PG1300, which is an intermediate resolution and where we can get the sodium deabsorption line. And for the second rating, it's a bit of a higher resolution. And for that, we specifically targeted the H-alpha emission line. In addition to that, like I've mentioned, we also have ALMA data available for some of these galaxies. One that I will show today, which is ISO 320 GO30. And this is just showing the moment 0 and the moment 1 map of this galaxy. So what then can we learn from these galaxies specifically? So this is showing the major axis kinematics of ISO 320 GO30, where we see the ionized gas, the molecular gas, the neutral gas, what the kinematics looks like, and also comparing that to the stars. So how did we do this? Okay. So first, in the magenta or in the pink, it shows the stellar kinematics. To do that, we modeled the stellar continuum with PPXF in order to extract the stellar kinematics, and that is shown in pink, like I mentioned. Then secondly, after subtracting the stellar continuum, we could model the sodium deabsorption lines in order to trace the neutral gas. Then thirdly, for the ionized gas, we modeled the H-alpha with a double Gaussian, and that is shown in blue. And lastly, for the galaxies that did have ALMA data available, we could then place a pseudo slit in order to extract the molecular gas. And then we can compare the ionized gas, the neutral gas, the molecular gas with the stars. For this galaxy specifically, what we do see is that the ionized gas, going to disappear, the ionized gas and the stars, they match with each other. So they are in the rotation of the disk, the narrow component of the ionized gas, but the neutral gas is basically just doing its own thing. At the center of the galaxy, there is an offset of almost 200 kilometers per second between the neutral gas and the ionized gas, and just off center at about 5 arc seconds, there is also an offset between the broad and the narrow component of the ionized gas of about 60 kilometers per second. And this all shows us that the neutral gas is not rotating with the disk. It's with the main disk, and also that there is clearly some ionized gas even that is not rotating with the disk. So it could be extraplanar gas, but it could also be an outflow. We also have a semi-minor axis kinematics for this galaxy, where we see something similar. Around the center, the offset between the neutral and the ionized gas is about 100 kilometers per second. And same thing around 5 arc seconds, there is about a 30 kilometers per second offset between the broad and the narrow component. For this galaxy specifically, it has been well studied by other researchers as well. And there is a known outflow along the minor axis, which we see traces of as well. And then just another galaxy that I want to promote is IRS 18293, which has been studied in a lot of detail as well, because it's a very interesting system. This has been studied by one of my supervisors, Dr. Moses Mokhotsi, in a similar way, but also with Muse data. There will be a poster presented tomorrow, so please go have a look if you do have any questions. And then just to conclude and to look into the future, for all all of the galaxies, and I've shown a few more rotation curves at the bottom for some of these sunbird galaxies. Like I explained in ESO 320 and also in these galaxies, we see that there is traces of either outflows or inflows or extraplanar gas, not just in the ionized gas, but even the neutral gas. And even if we compare that to the stars, it can tell us a lot about the fate of these galaxies specifically. As we all know, optical long slit spectra, yes, it is limited, but it has told us already a lot about these galaxies so far. But we are planning on looking at them with other telescopes, such as the newly installed IFUs on SALT, which I've mentioned, and MeerKAT. For the neutral gas, even though we can get an idea of what's happening using the sodium D as a tracer, it is also limited. And that's why radio data from MeerKAT is very useful. We have applied for, and hopefully our application will be accepted. And then lastly, with the new interferometers coming, like the SKA, it will help us even more because we can then match the spatial resolution to the optical data. So stay tuned for more results in the future.
Thank you very much. Thank you. Very nice talk. Questions for Pedro?
Thank you for that talk. Sorry if I missed this, but I know ISO 320 has an outflow, and I was wondering if you detect similar velocities or something in common in your different tracers.
Yes, similar velocities in the offset between the neutral gas and the ionized gas, yes, through other studies. But for us, we don't have the slit aligned along the minor axis exactly, so it's intermediate. It's between major and minor axis.
So do you say that in your sample you have several different stages of interacting galaxies? Do you think that the gas flows are most connected to the interaction of the galaxies or feedback from star formation and aging activity?
That's a good question. I'm not too sure yet, but I think it's a combination of both, because even for the galaxies that seems to be just sitting alone by itself, there's still some outflows or some gas that's not just rotating with the disk. So, both.
Okay. Okay, if there are no further questions, thank you very much, Pedro. And our next speaker is Ryan Keenan from the Max Planck Institute for Astrophysics. Talk show coming up. It's coming.
Oh, this is the.
That's your talk?
Okay. There we go. All right. Good morning, everyone. I am Ryan Keenan from the Max Planck Institute for Astronomy in Heidelberg. And this morning, I'm going to talk to you about the Arizona Molecular ISM Survey with the SMT, or AMIS, and in particular, understanding molecular gas conditions and the excitation of CO lines in nearby galaxies. Oh, sorry, this is an old version of the slides, but we'll make do. So to briefly give the background for why this is interesting, has already been established this morning that molecular gas is the immediate fuel for star formation. And in the past few years, in the past decade or so, we have learned a great deal about the connection between molecular gas and the star forming properties of galaxies. And this has been in large part linked to the things like the FANG survey that Adam talked about this morning, as well as other large ALMA programs that have both given us extremely resolved views of molecular gas in nearby galaxies, but also have allowed us to detect molecular gas out to redshifts as high as 6, sort of at the end of the epoch of reionization. And one of the things that has made this made all of this development possible is the extreme sensitivity of facilities like ALMA, not just to the CO line that has traditionally been used, CO1 to 0, but to higher energy CO transitions, so the CO2 to 1 and CO3 to 2 lines, which offer, which are brighter, but at higher frequencies, which means they provide a combination of greater sensitivity, improved resolution for a fixed instrument, and accessibility at redshifts beyond about redshift of a half. Unfortunately, we do know that is there a way to close? Yeah, thanks. CO2 to 1 and CO1 to 0 are not identical tracers of molecular gas. In fact, the ratio between the CO1 to 0 and 2 to 1 line varies as a function of galaxy properties within resolved disks of nearby galaxies, in the sense that denser, warmer regions tend to have higher CO2 to 1 emission relative to the CO1 to 0 line. What that means is that if we want to use CO2 to 1 as a tracer of molecular gas in these galaxy integrated studies, to do population studies of nearby galaxies, we really need to understand how these locally resolved trends extend to galaxy integrated scales. So does R21, the line ratio here, average down to some constant value, or does it vary as a function of galaxy properties? And to answer that question, we carried out the Arizona Molecular ISM survey, which consisted of CO2 to 1 observations of about 200 galaxies that we selected from the X-cold gas parent sample of galaxies, that were selected to provide a representative sample across a range of galaxy properties from masses of about 10 to the 9 to 10 to the 11.5 solar masses, and star formation rates from about 0.1 to tens of solar masses per year. We observed those with the SMT, which is a 10-meter, 7-millimeter telescope located in Mount Graham, Arizona, that can observe at 1 and 0.8 millimeters. And for these 170, 180 or so galaxies, we pursued sort of 5 sigma level detections of the CO2 to 1 line to match with the existing CO1 to 0 data, which, generally the spectra looks something like this. We also have CO3 to 2 for about a third of them. And that allows us to do population statistics on the ratio of the CO2 to 1 and 1 to 0 line. But not just population statistics, it allows us to explore trends in these lines with galaxy integrated properties. And what we find is that there's broadly no correlation with properties like stellar mass, but the star formation rates, we find a strong correlation between the CO line excitation and the star formation rate of the galaxy as a whole. So this correlation is present at about 6 sigma. If you model this accounting for just the statistical errors in the measurements, it's actually a very tight correlation. There's only about plus or minus 10% scatter at a given star formation rate. And this trend exists not just for star formation rate, but you can find similar trends for any property that's sort of tracing the intensity of star formation rate in galaxies, so star formation efficiency, distance from the star forming main sequence, star formation rate, surface density. And not only that, these trends match, at least in terms of their slopes, what is found in resolved studies of nearby galaxies. All right, so now that we know how this variation is happening, we can use that to determine what sort of the optimal R21 value to use for a given galaxy is if we want to get a molecular gas measurement, which converting from CO2 to 1 luminosity requires, to a molecular gas measurement requires first correcting for the ratio between CO2 to 1 and 1 to 0, and then multiplying the CO by the CO1 to 0 mass to light ratio. So we do this by taking this trend and extending it to a saturation at 1, that's thermal excitation of CO. And it turns out if you take previous samples of literature galaxies and put them on this plot, individual samples, it's very hard to pick out this trend. Right? The dynamic range of previous studies has been limited. They've focused on specific galaxy types. But as you add things they actually do fall nicely along the trend. And if you bin up each of these samples and just plot its median star formation rate and median R21, they all fall within the scatter of this relation. But what a MIST does that is unique is it allows us to link this range of star formation rates and especially extend it to lower star formation rates. So this is if you bin all of the data, including both the MIST and the literature samples, you see that there's now this nice trend. Another thing that we can do with this data is say for a matched set of observations of CO2 to 1 and 1 to 0 on exactly the same galaxies, do the trends between global galaxy properties and gas properties that we measure look the same. So what I'm going to show here is the correlation between distance from the star-forming main sequence and the CO to stellar mass ratio, so a proxy for the gas fraction of galaxies. I'm going to show it measured using CO2 to 1 and using CO1 to 0 and using CO2 to 1, where here I've assumed that there's a constant ratio between the two lines, which is common practice when doing this sort of work on galaxy integrated scales, right? And what we find is that the trends don't look quite the same. The slope that we would fit using CO1 to 0 versus CO2 to 1 is not exactly matched, even though we're looking at exactly the same sample of galaxies. And this extends to the correlation between distance from the main sequence and star formation efficiency. It applies to the Kinnick-Schmidt law. And the general sense of these trends is that if you try to measure the connection between gas and star formation rate of a galaxy using CO2 to 1, the connection that you find between gas abundance and star formation rate looks more linear, and the role of star formation efficiency appears to be less. So the effect of this, when you're not accounting for the variations in line ratio across the galaxy population, is that you change your answer in terms of how you interpret some of these scaling relations. So we also have CO3 to 2 for a handful of these galaxies. The following is preliminary, but broadly speaking, if you put the CO data or the CO3 to 2 data that we have on this plot, all of these same conclusions extend. The trends get more linear in mass, which suggests that CO3 to 2 is in fact very close already to this dense gas where there might be a linear trend between gas density and star formation. So Victoria Sambocco, a PhD student at Rhodes University who's been visiting MPIA for the summer, has been looking at this. It turns out that the changing slopes of the Kinnick-Schmidt law is an expectation of theory, and exactly what those slopes are can be used to get a grip on what the underlying scaling between gas surface density and star formation rate is. And more broadly speaking, we can use these collections of CO measurements for galaxies to try and understand the underlying physical properties of the galaxies. So sort of the next step for this work is trying to model the line ratios that we observe in each galaxy in terms of an underlying model for the density and temperature distribution of the gas. I'm working with Leonard Ugart, who's now at Leiden, on doing exactly this. I don't have results that I can really show yet, but as a preliminary sort of indication, here are the line ratios for the Amiss galaxies in color plotted against a grid of models from Adam Leroy's work, showing that systematically there are variations in the excitation of the lines, which correlate with variations in the density and temperature of the gas that we can use to extract properties of these gases. So as a closing note, I will say, there's still a lot of work to be done with just what we have now in terms of connecting these these global ratios that I've measured to what's happening in resolved regions of galaxies in terms of getting this modeling working. But in the coming decade or decades, what the NGVLA is going to allow us to do is make these moderately resolved or global measurements of CO line ratios out to high redshifts on a routine basis, which is going to provide insight into how the ISM conditions evolve over cosmic history, so that we can take these plots of the cosmic history of star formation or molecular gas abundance and start making them instead in terms of the cosmic history of gas temperature and density and the underlying conditions of the gas that is driving this global evolution of star formation in galaxies. So thanks.
Thank you. Questions for Ryan?
So this is super cool. Have you looked at correlation with the presence of a bar and so maybe a strong CMZ? Do you see anything if?
I haven't looked at that actually. I can. Cool. Yeah, it's a good idea.
Very nice results. Do you have enough IGNs in your sample to tell whether that also affects the R2-to-1 ratio?
There's a handful of AGN in the sample. There's nothing really conclusive that I can say, except that it doesn't look like it has a significant effect.
Okay, okay, I wanted to ask a question, but go ahead.
Sorry, just quickly. In X-cold gas, when we measure the CO, we need to correct for the aperture, which is like 45 seconds. So is there a mismatch between the aperture with your observations that could explain part of the differences?
I wonder if that slide is still there. Okay, so this is true. We apply an aperture correction to all of the data. The reason that we use the SMT in particular to do this is that the 10-meter aperture of the SMT and the 30-meter aperture of ERAM, which is where the X-cold gas was done, provide a matched beam size for the CO3 to 2 data. So there's no concern. For the CO2 to 1 data, our beam is a little bit larger than the X-cold gas beam. We've done a lot of work on understanding what exactly the effect of this on the line ratios could be. It turns out that assuming that gas, looks like the stellar profile of these galaxies on the whole, it doesn't introduce a bias in the line ratios we measure.
Okay, thank you very much. I think we need to move on. So the next talk is by Yuswan Teng.
This is not my slide.
Not the talk. Yeah.
Is there a pointer here? The blue. Thank you.
Talk is coming.
Just to say that the name of my slide is Elsa Teng, not Yu Xuan Teng, so that might cause some confusion, I guess.
No? Okay. Yeah.
Yeah,
Okay.
it's probably the name confusion.
Excellent.
Sorry about that. Yeah, so hi everyone. My name is Elsa Teng. I'm an incoming postdoc at University of Maryland and a recent graduate from UC San Diego. So I'll be presenting about my recent work on star formation efficiency and a new conversion factor prescription, which is a joint work with my PhD advisor, Karen Sandstrom, and the FANGS collaboration. So we know that stars are formed in molecular gas, which means that the star formation process is controlled by the amount of molecular gas and its star formation efficiency. So both of these quantities are important to understand star formation, and they can be studied through the well-known molecular Kaneka-Schmidt relation, which you can see from these figures that star formation rates have been found to be tightly correlated with molecular gas surface densities. And so this relation has laid an important foundation for many extragalactic star formation works, especially because the roughly constant slopes you see here are suggesting that star formation efficiency seems to be consistent throughout different regions or even different galaxies. However, to obtain either the star formation efficiency or molecular gas surface densities, we need molecular gas measurements. And we know that one big problem of current molecular gas measurement is they depend heavily on the knowledge of the CO to H2 conversion factor, alpha CO. So alpha CO is basically an empirical mass to light ratio that allows us to convert CO line flux into molecular gas mass. And many studies simply assume a constant Milky Way-like alpha CO in all kinds of regions or galaxies. But alpha CO actually varies a lot within and between galaxies. So for example, in this figure, you can see that alpha CO can vary up to orders of magnitudes in different metallicity environments. And also you can see that for galaxies like ULERGs, they typically have lower alpha CO than the standard Milky Way value, which is because alpha CO is also known to depend on CO emissivity related properties like gas temperature, densities, and opacities. And so you could imagine that in highly star-forming environments like galaxy centers or LERGs, they usually have higher excitation or turbulence that could bring their alpha CO to a lower value. So how would alpha CO variation impact our science? So first of all, it's important to know alpha CO not just affect the molecular gas itself, but also it affects every physical properties that are inferred from the molecular gas, which is a lot. So this includes star formation efficiency and a whole bunch of cloud-related properties. So this means that using a wrong alpha CO can really affect our, really even bias our estimation of many important quantities. And nowadays, alpha CO has already become the largest source of uncertainty in molecular gas measurements. So our immediate goal was to answer what exactly is the main physical driver of alpha CO variation among all these possibilities we know. And once we have answered this question, we can then think if there's a chance we can identify observables that can trace that main physical driver so that we can create a good alpha CO prescription that can be applied across large galaxy samples so that we can eventually come back and see how alpha CO correction will impact our knowledge on all these star formation properties. So as a first step to do this, we use ALMA to observe multi-band CO isotope log emission in 3 nearby barred galaxy centers. So we have 6 lines, including 12CO, 13CO, and C18O for each of these galaxy centers. And all these lines have an angular resolution of 100 parsec, which means it is at the giant molecular cloud scale. And we really need these high-resolution CO isotope log measurements because they allow us to derive detailed variations of alpha CO, as well as various molecular gas properties that are relevant to alpha CO variation. So we want to connect alpha CO with all these gas properties to see what exactly is driving alpha CO. And here is what we found. So first of all, we see a really tight correlation between alpha CO and the CO opacity, basically everywhere as long as CO is optically thick. And to the second order, we also see that alpha CO decreases with gas temperature. But clearly, you can see that the scatter in the temperature relation is much larger than the scatter in the optical depth relation. So it's pretty clear that optical depth effects are more dominant in driving alpha CO variation in these regions. And so our next step was to think, since now we know that optical depth is probably the main driver, is there a chance we can identify observational tracers for optical depth so that we can maybe use them to predict alpha CO from observations? So it turns out that we do see some clear trends of alpha CO decreasing with both the observed velocity dispersion and the CO to 13CO line ratio. So this actually makes sense because you could imagine that higher velocity dispersion could decrease the CO optical depth and lead to more escaped CO emission, and that will decrease alpha CO. And similarly, for the CO to 13 CO ratio, they can also trace CO optical depth pretty well because 12 CO is basically optically thick everywhere, but 13 CO is optically thin. So it looks like both of these observables can tell us something about alpha CO because they are reflecting the CO optical depth, which is the main tracer, with the main driver of alpha CO. But these are only results for 3 galaxy centers. So we definitely want to know if these relations can be extended well to more sample of galaxies with independent alpha CO measurements from dust, for example. And it turns out that we found the alpha CO relation with velocity dispersion is working very well on dust measurements as well. So here, the data in blue shows recent dust alpha CO measurement that covers 12 barred and non-barred galaxies, including galaxy centers and galaxy disks. So you can see this trend with cloud scale velocity dispersion match really well with the orange dashed line here, which is exactly the relation we saw on 3 galaxy centers. So based on this, such a good agreement, we have developed a new alpha CO prescription as a function of cloud scale velocity dispersion. So one notable thing about this prescription is that you can see the scatter around this prescription is only about 0.1 dex, and this is the smallest scatter among existing prescriptions. So we think this is because the cloud scale velocity dispersion here is directly tracing the physical cause of alpha CO, which is optical depth variations. So finally, we definitely want to know how these alpha CO variation would impact our knowledge of star formation efficiency. So we apply our prescription to 65 galaxies from the FANG survey, and we want to see how the derived Kennica-Schmidt relation will be different from using a Milky Way alpha CO. So from the figure, it's pretty clear that using our prescription would give a steeper Kennica-Schmidt relation in the galaxy centers, which suggests higher star formation efficiency. But on the right, you can see that using a Milky Way alpha CO simply give us a smooth and consistent star formation efficiency across the centers and the disks. And even more interestingly, we try to separate barred and non-barred galaxies, and we compare the derived gas depletion time using different alpha CO prescriptions. So first of all, we find that across galaxy disks, all the prescription we tested give us similar depletion time distribution, regardless of it is a barred or non-barred galaxy. So this seems like a good sign that all prescriptions are consistent. But interestingly, when we go into galaxy centers, we now see that clearly using a Milky Way or metallicity-based alpha CO gives much longer depletion time than using our prescription or the Blotto prescription, which both of us try to account for CO emissivity variations. And another thing that stands out is we find that only our prescription reveals a clear separation between barred and non-barred system. So this would suggest a shorter depletion time or higher star formation efficiency in barred galaxy centers. And so if this is true, this would actually change our current understanding, because you could imagine that previous studies using a Milky Way alpha CO tend to overestimate molecular gas mass in barred galaxy centers. So people used to think that the high star formation rate in these regions were due to the more amount of molecular gas, and star formation efficiency is constant. But what we found with our prescription is that there is actually similar amount of molecular gas between barred and non-barred centers. So it's possible that the high star formation rate is actually caused by the higher star formation efficiency, rather than there's really like substantially more amount of molecular gas there. So this brings up another interesting question, that what exactly is driving that increase of star formation efficiency? So one of our future direction would be to extend our analysis to the infrared wavelengths so that we can study the energetic stereo feedback that can be altering the star formation efficiency. So this can, for example, be done by JWST to directly observe the H2 gas and connect with the embedded star formation. Or we could also make use of the high JCO ladder from the far infrared emission to better constrain the warm molecular gas. And finally, another direction I'm also excited about is to systematically test the alpha CO dependence on the CO to 13 CO line ratio. So currently, we have only been able to do this on the 3 galaxy centers I've shown. And you might have also seen some new results on the antennae in today's poster session. But we haven't been able to really do this across large galaxy sample because having high resolution and sensitive 13 CO maps across many galaxies is just would take too much time. So in the future with NGVLA, we can expect this to be done more easily. And more importantly, it could even push alpha CO measurements to higher redshifts. So hopefully that will allow us to connect our understanding of alpha CO and all the star formation properties from low to high redshifts. So I will stop here and leave the takeaways. Thank you very much.
Okay. Thank you very much, Alpha.
So when you have a high delta V associated with a high opacity, I suppose you're assuming that's a single cloud. But if the beam has 2 clouds, or if there's high shear in the beam, then you could have lots of different clouds. And then couldn't they have an opacity different from the delta V? Because now the delta V is different clouds.
Sorry, you mean high delta V associated with lower opacity?
High delta V could be any opacity if the delta V is from many different clouds that are independent. Say because the beam has lots of shear.
Yeah, that's right. So that's why we find the delta V resolution we are using is at like near 100 parsec scale. So we find this to be really important. Like you need to approach the cloud resolution.
Bar non-bar comparison, is that true for your high Z extrapolations?
This one, you mean?
Yeah. Is that also 100 parsec resolution?
Yes, yes. All the delta V we're talking about is 100 parsec resolution. Yeah,
Related
from
question.
the Banks measurements.
A related question, is your delta V and opacity depending on inclination and how much?
Yeah, we do correct the delta V for inclination. So we account for inclination for each galaxy and apply a square root of cosine I to correct for inclination effects.
Any final question? No? If not, we'd like to thank Alpha again, and thanks actually all the speakers on this morning session. And that actually concludes the session. Alberto, I don't know if there are any announcements, or otherwise, see you in the afternoon. Yeah. See you later.
What do I do next slide? Do you know how you do the next slide in this?
So I think this is, that's laser.
Okay, our first speaker for the afternoon session is Roland Smith, who's going to be talking about the program.
Okay, so hello everyone. I'm Rowan Smith, University of St Andrews, and it's really lovely to be here. So I was given the task of reviewing the origin of cold ISM structure, which is clearly impossible in 20 minutes. So what I'm going to do is just focus on some of the broad ideas and look at what we can get from by combining simulations with observations from current and future facilities. And to do that, I'm going to start right down at the very beginning, the phases of the interstellar medium, which I'm sure everyone in this room is quite familiar with. But it's been known, obviously, long time, since back in the 60s with Ostrikers, that gas and galaxies exists at preferred phases in the interstellar medium. So if you look at the distribution in terms of number density and temperature, it clusters at key points. So this is the gas distribution in a simulation of a spiral galaxy. And you can see there are peaks, the yellow regions, at distinct temperatures and densities. Yeah, I'm too short for this, yeah? And the position in this space is determined the balance between heating from the interstellar radiation fields and local sources and cooling by atomic and molecular lines. So not just do we have a separation, however, in that phase space, but we also have a separation in terms of the spatial distribution of gas and galaxies. So again, this is from a recent simulation of mine. If you look at the H1, that covers nearly all the galactic disk. But where you look at just where the cold gas is, so this is the cold neutral material, and this is the molecular gas, you can see that it is much more spatially confined. It is clumpy. It is within your spiral arms with a little bit into the interarm regions. And what's really interesting is that although we take this separation between atomic gas and molecular gas, if you actually look at the distribution, it's near identical between that cold phase and the molecular phase, both in terms of its location within the galaxy and also in terms of its scale height. And so we can see that these two phases are really closely linked to each other. So how do we go from atomic gas to molecular gas? Well, again, it's facilitated by dust. We get H2 formation by catalyzed by dust and then desorption back into the interstellar medium. But the crucial process there is that once you form the molecule, you have to keep it in the gas, and it can be destroyed by the interstellar radiation field, which brings us to another crucial factor, that what we observe is CO, not molecular hydrogen, and the destruction of H2 and CO occurs at different column densities due to the different shielding of the two materials. So if you look at the column density of H2 versus CO, there's this big jump. And that means you have H2, which has no CO, and there is CO dark gas. Okay, so far, very introduction and very basic. What does this actually mean when you look at it into a dynamic interstellar medium environment? So this is from a paper I did in 2014. It shows you a section of a galaxy and where the molecular gas is in gray. And highlighted on top of this, in Barbie pink, you can see the CO emission, what you actually observe with your telescope. And you can see that the two things are not the same. And often we think of this CO dark material, this cold molecular gas, that is like an onion shell around about clouds. But this is actually not true. If you look, you see it extends far beyond the individual clouds. And so that's the first thing I'd like to make as a comment, is that when you form these bright molecular clouds that you see in observations, you don't need to always form them from scratch. A lot of the gas available to form that is already there, you just can't see it. And it only needs a little push to reach the densities where clouds form. And if we come back to that very basic plot of what the interstellar medium is, we have this idea, we have these very distinct phases. And it's true, we do. I've put them on this plot here. But that's not the whole story. There is also this gas between these traditional phases. So if you look, there's your warm neutral medium, there's your cold molecular gas, and down here's about where we form stars. You can see there is substantial material in between. And that's because of non-equilibrium effects. If there is a takeaway message from what I want to show you today about cold gas and galaxies, is that this is a dynamic equilibrium. It's not a static one. That there is flow within the galaxy. And yeah, the energies might match, but the gas is always moving between scales. And so there is not time to reach equilibrium. So you get material in this intermediate distribution. It also has a thickness, because within different locations within the galaxy, the local radiation field, the shielding, the metallicity might all be different. So what we can take from this is that the key thing to form dense gas is compression. Increase the density, the cooling becomes non-linearly more effective, and that's what drives the thermal instability to get you down to high densities. So what things can compress gas in galaxies? Well, the most obvious is galactic structure. When you see galaxies, we see these beautiful spiral arms that pop up really clearly in observations. So you can see here, some nice work by Claire Dobbs, really clear spiral, and in these spirals, you get cold molecular material. You can also do the same thing at galactic centers, where you have streaming motions along bars, impacting, compressing gas at the center, and just collecting gas in that environment so the overall density is higher. But again, that is not the full picture. Because the galaxy moves, you have shearing forces, and if you're collecting gas into a cloud and self-gravity is not strong enough, then that can be sheared and pulled apart. So for example, Sharon Might has worked on this quite extensively, showing that for a weakly self-gravitating structure, you don't need any external feedback. Simply the shearing motion of the galaxy alone is sufficient to destroy clouds over that timescale. Feedback, of course, also destroys. I'm going to skip over this because it's already covered by Adam, and Seth is going to be looking at this more later. But it's, of course, an incredibly important force in destroying cold gas in galaxies. But it can also be a constructive force. So while local feedback and supernovae can destroy individual clouds, what it is also doing is driving turbulence into the glass around it, which could destroy an individual cloud, where you then have converging gas flows driven by that expansion, which can collect new clouds together. So for example, you can see that in the simulations, if I hadn't pressed the wrong button. Very good. by Padua et al. And 1 million papers subsequent to 2016. But you can also see it in 3D dust observations, showing our local bubble. And if you look just in our own backyard, where you see the bubble expanding and intersecting with other bubbles from feedback, you see all the local star formation clouds forming at these interfaces. This can also be expressed in terms of a cloud-cloud collision. You know, when you have two gas clouds which intersect and collide, obviously the density increases and you form new things. Within the clouds themselves, we have these large-scale velocities, which then, of course, create shock fronts because it's supersonic within the cloud, and you get this dense network of filamentary structure within them. And so what I've done here is just rumble off a couple of things. Okay, all these processes can bring gas together. That's lovely. Everything is happening all the time, all at once. How do we deal with that? And this is where I think we're at an exciting point in this field, because those things don't all happen everywhere in the same way. If you look inside a galaxy, we can see these different ingredients to form the cold phase, to form stars, vary with galactic environment. Differential rotation, you have bubbles, you have metallicity gradients, different conditions at the galactic center, to the disk, to the arms. And so we have this natural experiment, which is happening within a galaxy, which allows us to distinguish between the key forces which are important for condensing gas. And we can look at this in theory. Got a few examples here. There are many others. So for example, in simulations by Robin Tress, he took a galaxy simulation, systematically identified clouds. And what you can clearly see is that at the center, the clouds are more massive. They have larger sizes. And so we can see this variation with galactic environment. Similarly, in my own work, I've looked at zooming into molecular clouds which were formed in coherent spiral arms compared to those found in a very cluster supernova environment. And what we find is that the internal structure is different. We get shorter filaments with a range of densities in the cluster environment, and this affects the fragmentation, with you instantly getting very large clusters and massive clouds forming along the spiral arm, whereas in the cluster supernova environment, it's much more distributed and sequential. And so we're getting different internal substructure, different densities, and different star formation outcomes dependent on these environments. We can see this also in terms of the star formation efficiency. This is some work by Ali in 23. And again, they took a galaxy simulation, zoomed into different regions within it, and looked at the star formation efficiency, finding it varied by 2 to 3, a factor of 2 to 3, depending on whether you are on arm or off arm. And finally, just to say this is not just in the molecular phase, you can also see the importance of the environment in the atomic gas. So this is again going to that 23 paper where I looked at the cold neutral medium. What I didn't tell you at the beginning was, although I could get everything right within the star-forming disk, outside the star-forming disk, it's a complete mess, because we know from ASCAP observations that there should be cold neutral medium out there. But this is something which we just cannot replicate in the simulations. And so this is showing us that in that environment, there is something we are not understanding in our models. And so galaxy environment matters. And this is where new observations really play into things. Because previously, our sample size for actually resolved molecular clouds was one galaxy, the Milky Way, within which we are deeply embedded and everything is an absolute mess. However, with the wonderful FANG survey and all the great work that's been done looking at nearby extragalactic sources, we can now study whole gas in scale of tens to hundreds of parsecs for the first time. And so we can look at these different environments and try and partition the importance of all these forces that I was just talking about. We can try and make progress in a more systematic and statistical manner. And here, of course, I plug again FANGs because I love it so much. And you can see the exquisite detail here
and all the different galactic environments which we can probe the different physics in. However, I have cheated because one of those was not real. Heads up to anyone who noticed that this one here was a nasty, dirty interloper, a simulated galaxy by Robin Tress put at the same resolution. And so we're at this point where we can now take simulations, transform them to the observational plane, and use the observations from facilities such as ALMA, MEERKAT, the SKA, to do this one-to-one comparison and do this natural experiment which nature has given us. And of course, this is going to get even better because what I've showed you so far was mainly molecular gas. If you look to my introduction, that transition between warm and cold happens first in the H1. And with SK, all its precursors, we're now coming into the regime where we can probe that crucial transition for the first time. So in my final 5 minutes, I want to think about this concept now of energy balance. Once we've got the cold material, what governs how it can collapse? Well, balance is crucial for the interstellar medium. It's been known for a long time that we have this pressure equilibrium which governs the formation of the phases. So for example, Wolfire in 2003 showed there's a minimum thermal pressure below which you can't trigger that thermal instability, you just can't push it together strong enough to trigger the compression. And more than that, in terms of the star formation, if you look at the work of Kim and the Ostreicher and the Tigris team, we see that that balance between the weight of the galaxy pressing down and the restoring energy and momentum that comes from feedback is crucial for determining the thickness of the disk and the amount of star formation within it. And so this balance is crucial. But as I said, it's not a static balance, it's a moving one. When we follow the path of individual clouds in simulations, we can see that they are constantly in flux. This is from Sarah Jefferson et al. In 21. And she tracked the individual parts of molecular clouds and found that the molecules themselves were only lasting for about 10 megayears. Instead, the cloud was being constantly replenished by fresh material coming in from the environment due to accretion, even as parts within the cloud were being destroyed. And again, this makes sense because when we look at the entire cloud, it is globally unbound. Again, this is work from Robin Tress. If you look at small scale structure within, where it crosses this binding threshold is only at densities of about 500,000. And that's a spatial scale of only about 1 parsec. And so these complexes which we observe are generally unbound, moving, and transient. And it's just these kind of 1 parsec size clumps within them which become unstable and can go on to form stars. And it's more than this, because when we look at the structure of the ISM and the transformation that has happened within the Milky Way, we see that this substructure extends from the very largest scales, where we have filaments on scales of hundreds of parsecs, right down to the 0.1 scale of star-forming cores, a continuous hierarchy of filamentary structures which are nested and connected within each other. And when we interrogate this observational relationship in more detail locally within the Milky Way, we see that individual clouds lie on scales within it, almost like lines, and this is like a superposition of different relations for different clouds, all of which are individually tight. And when we looked at this for the review of Hacker et al. In 23, we found that this balance could be explained by looking at accretion. And so there was a flow. Accretion onto these filamentary clouds from the galactic environment assembles the mass. The cloud then fragments, which would destroy it. But as long as you can accrete new material on fast enough, the structure remains there and is visible. And so it is this flow of material between the scales which is constantly happening within the interstellar medium. And again, this is something which we've tested in our observations, the paper by my student in 24, showing the flow of filaments in this observational space as they grow via accretion. Once again, this is where observations for extragalactic systems can now come into this dialogue for the first time. This is a paper by Filker et al. In 23, and we can see in the first bank results, we're observing and identifying these filamentary structures. So we can look at the connection between the large scale to the small scale. Now, the final point I want to make is about a dirty word, which I haven't said so far, which is very important. And that word is magnetic fields, something I ran away through all about my early career. Of course, the ISM is magnetized. And within clouds, which are strongly self-gravitating, you can probably treat that as a second order effect. But at the formation of clouds, if we look at these densities here, this is an important force. I would encourage everyone to look at this paper. It's by David Whitworth et al. It's a complete reanalysis using Bayesian methods of all magnetic field observations, including latest DCF results for the observational field strength relation between density and field strength within the Milky Way. It is not the Krucher relation, so that's very exciting. But you can see there is a substantial amount of magnetic fields at low densities. And we know this matters. So from the work of Juan Soler, we can see if you look at the flip of the orientation between the magnetic field vector and the orientation of filaments. Above, when the field becomes very strong, we see this flip where gas can no longer travel perpendicular to the field lines. And so we see a flip in the orientation between parallel to perpendicular, showing that there is an important dynamic effect underway. And so, just to finish, I want to abuse my privilege and talk about some work in preparation from one of my students. And what we did was we took a simulation of a dwarf galaxy and we looked at the energy balance everywhere within it, within the gas, to evaluate the importance of kinetic, thermal, magnetic, and gravitational forces to see where different forces dominated. This is where the magnetically dominant material is. If you think back to my introduction, let me help you. This is the warm neutral medium. This is the molecular medium. This here, right where the magnetic forces dominate, is the cold neutral medium, showing that during this process of molecular cloud formation, magnetic fields are really supported. And what will this mean? It will have this mean that this atomic reservoir, which is hard to observe, which is cold, can be supported by magnetic forces. It'll be more long-lived, and it'll have an important dynamic effect on that fraction. And indeed, in these dwarf galaxy simulations, what we find is that when you turn on the magnetic field, the star formation really doesn't change. That's set by the energy balance, the weight of the disk. But the molecular composition, the cold gas composition, really rises because you slow down with the magnetic field that process of cloud formation. And again, very excitingly, with new observations with H1, we're going to get a complete census of these galaxies and be able to look at that cloud formation process in great detail, which is very exciting. And so I leave it with this. These are my summary, my 3 points for where observations and simulations come together. We can see that the ISM is subject to forces that vary with environment. With new galaxies observations, we can test this. We can see that the ISM is dynamic, that things flow between phases. Again, with observations, we can test it. And we know that magnetic fields are important. With observations, we can test it. Thank you.
But I can't figure out how to turn it on.
Okay. This is totally fine to duck if not, but I mean, you're showing dust images and then you're showing, and you're comparing these to gas. And do you want to say a couple words about the prospect to get realistic dust flowing through all of these things and whether that might matter or whether or not, or?
I mean, we're basically assuming that the dust and gas distribution are following a constant ratio. To be honest, dust is super easy from the simulations. It's really lovely because it does follow the general density distribution much more closely. So actually comparing to dust is much more easy between the simulations and observations because you are following the full distribution with less radiative transfer effects.
So you would predict being able to see all of this CO dark stuff just as pieces of the WSP images.
Exactly.
Any more questions? Yes. And can we go ahead and switch to the next talk up on the screen? Can we put the next talk up?
Could you explain a bit more at a given surface density why inter-arm regions have lower star forming efficiency than the arm regions?
I'm not sure because it does seem to be, it's a factor of being 2 or 3. But yeah, it's something I'm looking at the moment. It does seem to be there in the simulations. The work I showed you was by Ali et al. And again, it was more due to the size of the clusters. And his things, he was finding that in the spiral arms, the clouds were larger, and you could imagine they were more self-gravitating, harder to destroy by internal feedback. But this is something I'm also looking at the moment in my own work and a range of different environments. And so, yeah, it's in progress.
Do you expect dark gas at low metallicity in dwarf irregulars to be H1 or H2?
I would expect it to be mainly H1, but there will be H2. We've done some work in this in low metallicity galaxies with David Whitworth, looking at metal poor galaxies. Where do the stars form? Because we thought it might be just purely in the cold atomic gas. But we found even in those systems, the actual star-forming cores were molecular. It's just they're very small, kind of almost like it's only the individual core scale which is molecular within the metal poor dwarfs. The cloud itself is atomic and just the cores are molecular.
Let's thank Rowan again. That was great.
That was such a fantastic introduction that I feel like I don't have to give the first couple of slides of my talk. And apparently I'm slightly taller, but so I'm going to talk a little bit about what we see in H1 in the Magellanic Clouds and the Milky Way using gas gap H1 observations. So I'll try to figure this out. Whoa, uh-oh, that was a new one, sorry. Okay, bad me. Okay, exciting. So I'm not going to spend time talking about the importance of H1 in a galaxy, but I'm going to talk about the very last point, which I put into bold. So we've just heard that H1 is the main reservoir out of which the giant molecular clouds form. So how do we know where the H1 is cold is the question that we're trying to get at. It's not always trivial to get at whether the fraction of the H1 that you see is warm, which it could be then 5,000, 6,000, 7,000 Kelvin and of no use to you in forming molecular clouds, or it could be 20 Kelvin and be very useful in forming molecular clouds. So the key thing that we'd like to know is how do you figure that out? And that is somewhat fraught. So this was just to show that we trace H1 in lots of different places, but I'm not going to go through that because we often assume that the H1 emission line width tells us about the temperature of the gas. So you measure a H1 emission spectrum and you fit it with some Gaussian and you say it's narrow and maybe it's got a line width of a few tens of kilometers a second or 10 kilometers a second. But line widths are very misleading. If you take a line like that, where would you tell me that the cold gas is in velocity space? Is not always easy. But if we measure H1 in absorption, it becomes a lot easier because the absorption is much, much strongly linked to measuring the cold gas. So we take an absorption spectrum, and this is the same line of sight, and we see that there are two cold components along that line of sight. They're unambiguous. We know they're there. We know it's cold. Well, that's very nice, but you have to have absorption against a bunch of background sources, and that's not always trivial. And the other reason that this is important, wow, things really move around when you translate them from one slide format to another, is that but in the top one, if we assume that the H1 is thin, optically thin, then you measure its column density to be one number, but if you have an optical depth measurement for that, you get another number. So if you want to know either the temperature of the gas or its actual density, you would like to know whether it is cold and optically thick or not. And one of the things that we're trying to do with observations now is to be able to answer that. So this is from a compilation of data that I put together for an annual review last year. And this is looking at various different simulations, a few different ones that show the distribution of the cold gas temperatures, the unstable that we've just heard about, and the warm up here. And using absorption lines, we can measure the temperature of the gas to probe the cold portion down here. And one of the things that we can see is that if there is more shielding, it skews towards the colder end. If there's less shielding, it broadens out the temperature distribution. So the amount of shielding is also relevant to what the temperature of the gas is. But knowing how much lies in any of these different phases is tricky because, as I said, this is absorption. Trying to get this end of the distribution is a lot harder. You can't do that so well with absorption, and we don't do it even that well with emission. So one of the things that we're trying to do is to get at these problems. Where is the cold H1? How is it distributed? What are its temperatures? How much cold gas is there in the galaxy and in the Magellanic Clouds? So this has led us into the GasCap H1 survey, which is covering the galactic plane in the southern hemisphere. It's covering the Magellanic Clouds and the Magellanic Stream, and we've lost the leading arm observations. High sensitivity, high spectral resolution, and high angular resolution in both emission and absorption in order to try to fully characterize the H1 content. So just to give you, this is an old slide too. Darn, I had such a beautiful image. Come and see me later and I will show you a spectacularly wonderful image. But this is from the GasCap H1 LMC shallow pilot. This is a peak intensity map. This is 6 ASCAP pointings over the entire LMC. And this is shallow in the sense that it's only 10 hours of observation per pointing. We'll be going a factor of 20 deeper in our observations as we come up. But already you can tell when you zoom in the level of detail, these very, very fine structures that are all over the place, we're now looking at with ASCAP in its shallowest form. Okay, we're going to try to go forward. There we are. In the same area where we are measuring the H1 in the Magellanic Clouds, we get the dirty window in front of it, which is the Milky Way. This is the foreground Milky Way to the LMC, and it should have looped, but it didn't also. So let's see if we can go back and then go forward again. So you can see Milky Way diffuse emission across our entire pilot region there. And we're using this to try to understand what the temperature distribution of gas is. So this is some work I'm going to highlight from Van Heep Nguyen, who is here, and you should talk to him. He will also be giving a talk next week. In the past, we had in this image about 360 H1 absorption measurements across the entire Milky Way to give us the spin temperature. And the positions are shown there. You can see these points here, distributed about with a very nasty hole in the southern hemisphere. Now with ASCAP, with that foreground measurements that I just showed you, we're looking at this little boxed region here. HAPE has been able to detect 460 absorption line measurements. So we've just more than doubled the total number in the Milky Way, but now in a region that's only about 30 by 30 degrees across on the sky. And back in 2015, I wrote an article for the SKA science book that said the great thing we're going to be able to do with the SKA is that we are going to be able to measure the temperature distribution of gas in the Milky Way across the whole sky by taking absorption line measurements. And I feel like my dream is starting to come true here with these ASCAP measurements. So we can measure all the way across this area, and these are measurements of the temperature distribution there. So you can see there's some warmer places, but in general, it's of order 100 Kelvin, and it seems pseudo-random. Doesn't seem to be clearly linked to where the column density is. So now the next step is, where do all the effects come in? What's the interstellar radiation field? What's going on? How do we understand why the gas temperatures are what they are? The detection, however, is a strong function of column density. Where the gas is more than about 10 to the 21, you tend to detect it in absorption per atoms per square centimeter. Where it's less than that, we tend not to find it. And we're averaging about 2 sources per square degree now in our measurements. Moving quite quickly along. So this is the spin temperature distribution. Trying to unravel things like sensitivity, or it makes it tricky to know exactly where the gas temperature is, but we're working on that, and Heap can tell you lots more about it. So along the same sight lines, we also have the Magellanic absorption. So where is the cold gas in the Magellanic system? And these here, all of those dots that you can see, are measurements of absorption in the Magellanic clouds and along the Magellanic Bridge. And so now we're able to sample not just how cold gas looks in the Milky Way and measure its temperature, but to do it all the way across the Magellanic system. And you can see that there is absorption measured through the Magellanic Bridge as well. In the SMC itself, I'll just focus in a little bit. So this is looking at the SMC work by James Dempsey et al. And these squares here are all the detections, and the circles are places where we've looked but didn't see anything. And again, that's just one ASCAP pointing. I circle these 2 regions out here because in most places where you see absorption, you see that the column density, which is what's in the background, is reasonably high. But these 2 little places out here, it doesn't look that high. So if you were trying to search for absorption without knowing anything about the distribution of the gas other than just its column density, you would not think that you would find them there. But in fact, we do. We see a number of detections that are way at very low column densities down here in this distribution. So Antoine Marchal has, has developed a method for producing a finder map for looking for where you find cold gas. So you take a column density, or you take an H1 cube, you take an FFT spectrally, and you can produce a lower limit on the cold neutral medium fraction. And that's what's shown here. And then if you compare that to the H1 in absorption, you find that all of your detections sit where you've got little cold clumps that are shown in this finder map. So if you don't have an ASCAP where you have a 30 square degree field of view, this is a good way to know where you should look for H1 in absorption. Okay, so before Deanne beats me up, I'll just summarize. H1 is an important throttle in the evolution of the ISM, and Rowan told us all about that. But its temperature is a complicated function of the heating and cooling. And to measure it, we really need to know its temperature. So we need absorption. The wide field absorption surveys that we can do in the Milky Way and the Magellanic Clouds now are set to sort of revolutionize how we study the properties. We're no longer guessing at the temperature of the gas from the H1 emission, we're measuring it. And we're measuring it with a sensitivity or a sampling that is equivalent to how we were measuring in H1 emission 15 years ago. We're getting 2 sources per square degree or so. So from that, we can also get the optical depth correction so we can know how much gas is actually there. And of course, SKA will take this to other galaxies. That'll allow us to push out further. And we're already starting to see hints of that from JVLA and Meerkat, where we're moving towards absorption line measurements in other galaxies. Thank you.
Thank you very much for your talk. Could you maybe go back to slide 7 or something?
Maybe I could.
Okay, no. Okay, so there was a slide with the map of the Milky Way, and some of the points had up to 10 components. This one, yeah.
Oh, that one, sorry.
Could you just, what do you mean by components in this?
So these are spectral components. So the problem with measuring H1 absorption through the disk of the Milky Way is that.
Any other?
I'm curious about the FFT-based cool neutron medium finder. Is it in the velocity space alone or spatial and velocity together?
No, it's in velocity space. And Xinzhong, who's giving a talk in about further on, will show you a little bit of work from that as well. But yeah, so it's just working off of the H1 emission line width, which we know is dubious, but it's enough to give you some idea of where the cold stuff is.
Let's thank Naomi again.
Nice. Perfect. Hello, everybody. Today, I'm going to talk to you about some work I did with Jungyu Kim, Changgu Kim, and Eve Ostreicher, who are all part of the Tigris collaboration. I really want to shout out Jungyu Kim for this work, especially with the numerical methods, as we discuss how we used ray tracing to explore UV radiation fields in these simulations of the multi-phase ISM. So the Tigris simulations have gotten a couple shout outs in the past few talks, but what are they? So these represent simulations of patches of the ISM. Here you can see the footprint of our solar neighborhood model. So looking at the face-on view, it's a wrong button. It's a 1 kiloparsec square patch of the ISM with a vertical extent of about 7 kiloparsecs. And with this, we can get really high resolution simulations of the multi-phase ISM with plenty of physics included. So there's a lot included in these simulations based on the work of many people, but some of the important things are full cycle of star formation and supernova feedback. There's photochemistry, including non-equilibrium hydrogen photochemistry, and updated heating and cooling of the gas. But what we're focusing on for this study of UV radiation is a new novel approach to radiative transfer, which is using ray tracing. So we start from the source particles in the ISM, and from each of these source particles, we follow many, many rays of UV radiation, which travel out throughout the simulation box and interact with the gas and dust to self-consistently solve this equations of radiative transfer. And we follow two bands of UV radiation. So we have, I keep hitting the wrong one, far UV radiation, which is important for molecular dissociation and photoelectric heating, and also Lyman continuum radiation, which is important for the photoionization of hydrogen. And when you put all this together, you get nice movies like this. So this is the 1 kiloparsec face-on patch of our solar neighborhood model. In the top left, you can see the gas phase, so all the way from hot, the warm medium, down to cold. You can see different gas parameters, like temperature and density. And in the lower right, you can see the FUV radiation field and the Lyman continuum. And here you can see what's really great about radiative transfer, which is you can see shadows in the FUV radiation due to dense gas, as well as these bright sources that are appearing. And in the Lyman continuum radiation, you can see where it's completely absorbed by the neutral medium and you see no radiation whatsoever. Now, there are plenty of things that we can do with these simulations, and I have looked at them, but just to summarize, what we might do, for example, is characterize the distribution of FUV radiation throughout the simulations, which could be useful to compare to observations. We can find approximate models for the UV radiation, which might be useful when you're doing simulations and full radiative transfer with ray tracing isn't possible. We can look at the ionization parameter and the ionization state of the gas throughout the simulation and also in different environments. But because I have only 10 minutes and I have to choose something to focus on, what I'm going to talk to you about today is how you can look at synthetic maps of dust emission. So we know at its most basic that dust absorbs far UV radiation and re-emits in the IR with complications that I'm sure all the observers in the room know about. So we don't follow IR radiation, but we do follow the far UV, which means we can roughly characterize dust emission using a convolution of the local FUV radiation and the local density. This, of course, makes assumptions such as a constant gas to dust ratio. But you do produce a map that looks something like this. So imagine that this is a face-on view of a beautiful JWST observation of mid-IR emission. And as we've heard a few times now, that dust maps can also be used as gas maps. So because we have full information about these simulations, we might say, how does this map of dust emission compare to the gas distribution? So here we can compare directly between what we say is our dust emission to the column density. And you can see these are pretty similar. There is definitely some similar structure between the two maps, but there are differences, particularly around sources. So when there's bright FUV sources, you might expect to see more dust emission than what would be expected to see in the column density. One question we might ask then is, can we correct for this non-uniform radiation? Can we go from this map of dust emission to the column density, which is also something you might want to do in observations? So we know what the FUV radiation is in our simulations, but in order to do this in observations, you might need a simplified model of the radiation field. One way we can do this is to look at the individual sources. We actually considered a few different FUV radiation models, and this is what we found to work well in this case. So a very simple way to model the radiation is to say, take each of our sources. We know the luminosity. We know that there's some geometric attenuation as the radiation travels from these sources. And we also know that there's going to be some absorption by dust. Here on the right, you can see our comparison between the actual FUV radiation field from the ray tracing to this model. And of course, there are some differences. In the dense gas, we overestimate the radiation field, whereas near the sources in the brightest regions, we underestimate it. And that's partly because we have to assume some constant density because you wouldn't know the local density as you go throughout the region. But using this model, we can say, can we then get a better estimate for the column density? So what you can do is say, let's say that our estimated column density is some combination of the dust heating, the dust emission that we see, and then we take out our model of the FUV radiation. And then you do need some normalization between what you expect to see from your dust emission to the column density. One thing that you might do is say, do we have any knowledge of the column density whatsoever? And use that to normalize. And this might be possible with observations of the column density using, for example, 21 centimeter. So taking this all together, we start with our dust emission here on the left, where you see these very bright sources. We do this correction to get this middle map, which is much closer to the actual column density that you see. Of course, me showing you one snapshot does not prove that this approximation works, but we can look at it statistically. So here we have some 2D histograms of the overall distribution with the column density on the x-axis. At the top, we have this dust emission, and at the bottom, we have our estimated column density. And I'll point out that at low column, the dust alone is a very good tracer of the column. The dust emission is a good map of the overall ISM distribution. But at higher densities, where you have, at higher densities, you're going to overestimate the column due to the non-uniform radiation field. And therefore, when we apply our FUV radiation model, we can get better estimates at this higher column density. Of course, the overall calibration to fall along this one-to-one line between the estimate and the actual column relies on some knowledge of the column density to get the overall normalization. But this is promising as a way to go from dust emission to column density. Because it is relevant, and I only have 1 minute left, I will do a shameless self-promotion of my poster on Friday. because it is entirely relevant. In these same Tiger simulations, my actual thesis work is looking at the transport and spectral evolution of cosmic rays, which I'm able to use to produce mock observations of synchrotron radio emission. So these are very useful comparisons to next generation high resolution observations of synchrotron radio emission to study the connection between the cosmic ray distribution, the magnetic field, and the column density. With that, because I'm out of my time, I will say that these are the Tigers NCR simulations with UV radiated transfer using ray tracing. And these have many, many applications, which I'm happy to talk about with anyone here. But in particular, one application is to connect dust emission to column density. And with that, I'm happy to take any questions.
Thank you, Nora. Do we have questions? Go over here.
Hiya, thanks for the talk. Do you have any treatment for scattering in calculating the dust emission field?
In this case, no, because this is a very basic approximation of the dust. It's using just a, yeah, no scattering, just a constant gust to dust ratio.
Of course, dust temperature gives you quite a bit more information too, if you've got a single cloud, single line of sight, etc. How does that fit into this story? Does it help or give the same similar information?
Any more information would be helpful. This is just a first order approximation of what we can do with these simulations because they just have global dust parameters. There's not local dust parameters in this simulation. Yeah.
Hi, thanks for your talk. Have you tried to compare synthetic SEDs, spectral energy distributions, to something like a standard or a piece of a nearby galaxy?
That'd be great to do because we don't have a dust population model. We're just doing some assumption of constant gas and dust population. It'd be really difficult to make an SED using these simulations. We can make SEDs using the cosmic ray distribution, but not with the dust.
So my query was about this basic assumption of gas to dust ratio, which we always make.
Yep.
And then if things change near the UV radiation field, then that will be an added complication. How do you anticipate things to change?
Oh, I mean, as you add more complications, I don't want to make a prediction of exactly how this will change, but of course, every added complication will change the distribution of this dust heating that you see. So because we're assuming a constant gas to dust ratio, we're not getting additional scatter in the dust observation compared to the column density in the simulation. But if you have varying gas and dust populations, you would expect larger variation.
Any last question? No, let's thank Nora again.
Hello everyone, I'm Shinjung Kim, a second-year PhD student at the Australian National University. Expanding shells are pretty common in galaxies, likely driven by supernova or stellar feedbacks. So today, I'd like to talk about the cold H1 gas formation in the Magellan Bridge, driven by these expanding shells. So cold H1 is the precursor for star formation. We need to understand the cold H1 if you are interested in the star formation. So the interstellar medium ISM has a mixed multi-phase gas, and there are two primary stable phases. The warm neutral medium, which is diffuse and warmer phases, and the CNM, the cold neutral medium, which is cold and denser phase. And also there's an unstable neutral medium between these WNM and CNM. And in the Milky Way, through observation and H1 emission studies, we have known about these mass fractions of each multi-phase, but these multi-phase fractions and properties vary in different environments. And also, this LMC and SMC, through H1 observation lines, we have known about the coordination properties, but we don't know about the Magellanic Bridge. Where is the CNM, or how much is the CNM? We don't know about this. So in our study, I'd like to investigate the Magellanic Bridge. So shear structures driven by stellar feedback sweeps up and compress surrounding gas and triggering gas condensation and U-star formation within these shear structures. So in the left figure shows the Magellanic Bridge core shear structures. Here the background is the gray is the stellar core, and here is the contour is the H1 column density, and we can see here the low column density H1 core, and the higher column density region matches well with the shear structure, showing the H1 shells expanding, and it triggered new star formation in the Magellanic Bridge. So we know that star formation is happening, but we don't know about the multi-phase properties in the Magellanic Bridge. And the right figure shows the H1 gas distribution of the large Magellanic Cloud, and the red contours shows the supergiant shells in the item C, and where the enhanced molecular gas clouds has been observed. So can we observe the enhanced CNM, and how is the distribution of the CNM in shear structures? I like to answer these questions. So using the CASCAP H1 observations, I get the opportunity to investigate the Magellanic Bridge. Here, the Magellanic Bridge is a tidally stripped gas stretching between the two clouds, NMC and SMC, and it's a low metallicity environment. And also, it hosts star formation. And this figure shows the H1 peak intensity map of the Magellanic Bridge. It shows bridge's dynamic structures. It hosts filamentary loops, and it hosts 163 shear catalogs by Muller et al. 2003. So the Magellanic Bridge is a very complex environment. So now we show the lower limit of the cold H1 column density distribution in the Magellanic Bridge from Fourier transform method to FFT method, like Naomi discussed earlier. So this FFT method is exploit the narrow line of the H1 emission. So the narrow line means presence of the cold H1 gas. It's developed by Marshall et al. So please read this paper. So this figure shows the cool H1 gas distribution in the bridge. And here the magenta crosses indicate the molecular clouds from Mizuno et al. So it indicates the spatial correlation between the molecular clouds and cold H1 in the Magellanic Bridge region. Of particular interest is this H1 shell. We can see the cavity here, and it's abundant in cold H1. So this H1 shell associated with the H-alpha ring DN171, and it's identified by Muller et al. 2003. So this shell is driven by supernova or stellar winds from all stars, and also it's expanding with 5 ± 2 km/s. So, like I said before, can we observe the enhanced CNM, and how is the distribution of the CNM in these shear structures? So we know that this shell is abundant in H1 from the presence of the narrow line, but for more kinematics, we decompose the H1 emission data into multiple Gaussian components. Here, the magenta cross indicate the molecular clouds in the shear boundaries. And here, the dashed vertical line indicates the CO peak velocity. It matches very well with the narrow Gaussian component, which is classified as a CNM. So it means that kinematic association between the CO and CNM in shear boundaries, and also the molecular clouds is forming from the CNM component in the shear boundaries here. And also from profile decomposition, we classified as CNM, UNM, WNM components based on the velocity divergence. So here are the integrate intensity maps of each multi-phase. So we can see difference in structures. For instance, when we look at the CNM, it shows the small scale structures in the shear structures. But on the other hand, UNM components shows smoother plus structures compared to the CNM. But for WNA components, it shows not significant H shell structures. Then we also obtained the mass fractions of each multiphase. Remarkably, a little WNM mass fractions is found like 10% in the shell structures. But on the other hand, the CNM or UNA components contribute much. So it means that the stellar feedback driven by the shell expansion driven by stellar feedback trigger thermal condensations, and phase transition is happening in these shell structures. So now we show the multi-wavelength view of the stellar feedback-driven shell. So from left to the right, we show the H1 peak intensity map and the CNM H1 column density from the profile decomposition. And the third panel shows the H alpha, the ionized region. And the last panel shows the 250 micron cooled dust. So when we look at the first panel, we can see the clearly cavity driven by stellar feedback. And when we look at the second panel, it's abundant in cold H1 properties from Gaussian decomposition. And here the magenta circle shows the molecular clouds from 12 CO lines. And also here the colored stars indicate the young stellar objects. So it means the shell expansion driven by stellar feedback triggered the CNM formation and molecular cloud and further trigger new star formation within the shell. And the third panel shows the ionized ring DM171. So it triggered the shell expansion here. And also the cold dust emission swept up in these shell structures. And it's especially correlated with the molecular clouds and the CNM properties. And now, to better understand these H shell mechanisms, we have looked at the large scale structures again. And then we found that these H shells is found of the larger shell structures here. So this shell is 450 parsec in diameter, and there are two smaller shells located in these regions. So far, we investigated this shell, the DEM171 shell. And now let's look at the another shell, it's part of the larger shell structures. So from left to the right, we show the H1 peak intensity map and CNM and H alpha and cold dust. Here the two blue stars. Here the two blue stars are the O stars. In the center is likely ionizing sources for this H alpha. And also the colored stars are the young stellar objects, and they are present at the shell boundaries. So this shell also, the expanding shell also triggered the CNM in the shell boundaries and young stellar objects. So now we propose a sequential shell formation in the Magellanic Ridge. And this research provides a baseline study for multi-phase ISM based on profile decomposition and interplay between the stars and gas in diverse environments using the CASCAP H1 observations. Thank you.
Questions? Sorry.
Do you have any idea about the ages of these shells? And is there some X-ray component that can give us a hint on the content of hot gas?
Yes, actually, I investigated the dynamical age of the H1 shells around the 10 mega year. And also I have a look at I show the young stellar objects. Can I show? For instance, this H1 shell is dynamical age of the 10 mega year, and it matches well with these O stars in the center. It's around 8 or 9 mega year. And also we have some young stellar objects in the shell boundaries, and it's younger than the H1 shell. So it shows the sequential new trigger star formation in this system. But I can show you later, yes.
Any more questions?
Thanks. So when you do the filter, the separation of the different components and find a surprisingly small amount of warm neutral medium,
Yes.
you know, you might expect that to also be more spatially smooth than some of this cold stuff. Is the filtering of different spatial scales a concern here? In the interferometer data?
So you mean the spatial resolution can affect this?
When the warm component you might expect to be spatially extended so that, if you don't recover those scales as well with the interferometer, I don't, the Magellanic Cloud is very large, so I don't have a great sense of whether you'd be worried about losing some of the flux on that scale, is explaining why the warm neutral medium is so surprisingly low.
It's hard to answer for that.
Yeah, don't worry about it. We
Yes,
can chat
yeah.
later.
Yeah, we can chat.
Any last questions?
I'm wondering if you put a PV slice on top of your shells, can you observe outflowing clouds on top of the shell center around in the shell region?
So you mean the mixtured structures within the shell?
Yeah, can
Yeah.
you see the signs of outflow?
Outflow?
Yeah.
Outflow shells?
Outflow of clouds within the circle of the shell.
We can chat later. So,
Thank you.
Yeah.
Let's think again.
Oh, great. I thought I had to dance my talk. It's the big one. Okay, and to go back? Okay, great. Thanks a lot. It's a great pleasure to be here. And I'm going to be talking about another aspect of connecting the molecular clouds and the diffuse environment. And it's using a new technology, probably the biggest revolution that we have in our understanding of the ISM, and is the 3D dust maps. So before that, let's check what it means to match or to link the molecular gas with the diffuse ISM. So as you heard from Naomi, this is the H1 samples the diffuse ISM that is around and in molecular clouds. Is the pre-molecular state and most likely the reservoir from which molecular clouds are formed. The main tracer for that is H1. The main tracer for molecular gas is CO. So far we have been seeing lots of scattered plots. We have been seeing lots of relations, but there's a piece of information that we haven't been using, and is, do these things actually look alike? And can we actually learn something from that? So let's give it a try, okay? So how do you link two images and say that they are alike? You as an astronomer, you can put the two images next to each other. This is one of the best maps that we have of molecular cloud. This is the Taurus molecular cloud, and 140 parsecs from us. If you take all of the velocity channels from H1 and CO and look at them for 1 second and compare them all, it would take you 1 hour to compare all of the images here. So this is not something that you can do by hand. So you need something else. And I propose you to do it this way. So there are two images here, and they have something in common. I'm not going to tell you what they have in common, but they have something in common. If you Google an image, if you have ever Googled an image, what Google does, the first thing that it does is characterize an image by its gradients. So it highlights the places where you have bright changes in intensity. Other thing that they do is not look at the gradients themselves, but at the orientation of the gradients. So you can see where the gradients are pointing at. And then you can compare the orientation of the gradients. It turns out that if two images actually match, the gradients are parallel. So that's a way of comparing many images at the same time. Of course, you cannot do this kind of maps all the time because, I mean, you're just going from two images to one image. So you do a histogram. That's why this method is called histogram of oriented gradients. But then you don't want to see 1,000 histograms. So there's a metric to actually check how big your histogram is around 0 degrees. You know, if the two images are completely uncorrelated, your histogram should be completely flat because the gradients don't know anything about each other. If the images have something in common, you have a peak around 0. because the gradients are actually matching. So how do you measure that? You use this thing called the projected Rayleigh statistic. This was invented by Lord Rayleigh and then modified during the 20th century. So this is like a sigma that tells you the significance of the departure from a flat distribution of angles. This is the projected Rayleigh statistic. It's called projected because it has the number 2 for historical reasons, basically because I was working on magnetic fields before. So you can actually make maps now of the velocity channels that match between your two tracers, in this case, H1 and CO. So this is an example. This is from the Thor survey. And here what you're seeing is, in the colors, you're seeing the correlation between the morphology of H1 and CO. So in the x-axis, you have CO. In the y-axis, you have H1. And actually what you're seeing is that H1 and CO match. Where's my pointer? I lost my pointer. They match at the same velocities. So H1 and CO are co-moving, and they're also co-spatial. They look alike. They wouldn't look alike if they were not co-spatial, and they're co-moving. So this happens for a big portion of the galactic plane. This is a 2 by 2 degree tile, but that is not what happens everywhere. So how does that look? You see here, H1 emission, and this is CO. What actually we're seeing is that the H1 matches the CO, where actually there's a decrease of H1. This decrease of H1 is not caused by the depletion of the H1, but by actually a line of sight effect. You're seeing the cold H1 that is related to the molecular cloud seen against a hot background. So you see this effect that is called H1 self-absorption. The H1 in the H1 self-absorption actually is matching the CO. When you split that map, that general map, into small portions, you find that in some places you are actually co-moving. H1 and CO are moving together. But in some other places, you have an offset. Sometimes we find some offsets of a few kilometers per second. So the H1 and the CO are not moving together. They're co-spatial because they look alike, but they're not co-moving. You have an offset. And this is hard to disentangle in the galactic plane. Those offsets tend to be of a few kilometers per second. So how do you actually build something out of this? Is this the feedback that is moving one phase with respect to the other? The advantage is that for the nearby ISM, we have 3D DOS maps. So how does that look? So this is the same example. This is the Taurus molecular cloud at 140 parsecs. Here, you not only have the H1, the CO. Actually, you can see here this shadow of H1. Actually, that's the cold H1 that is related to the molecular cloud. You have the 2D dust, so the standard dust that we get from submillimeter emission and from extinction. But now we have the 3D dust that is recovered from extinction measurements and stellar parallaxes that we obtain with Gaia. So you can actually model the nearby ISM in 3 dimensions. So that is a new dimension that you have. How does that look? For Taurus, it looks like this. This is the reconstruction for Reimar-Leike. So this is already 4 years old. I'm going to show you some more new reconstructions. And you can see that some of the structures that you see there as filaments actually belong to a deeper network of structures that are all nested into the diffuse ISM. So what did we find when we applied the H1 and the CO and the 3D dust? Well, you can do exactly the same mapping. In this case, it's not a velocity to velocity mapping. It's a distance to velocity mapping. You're assigning distances to velocity. Wouldn't you like to do that with your external galaxies? Of course, it would be great. For now, we can only do it for nearby galaxies, for nearby molecular clouds. But there we found, in this example, this trend. We found that the most nearby part of the cloud is moving faster than the backside of the cloud. So that means this cloud is being compressed. So that's very cool. So it looks like that. And actually it corresponds to what we know about the nearby clouds. Most of the nearby clouds are being sandwiched between the local bubble and some other bubbles. So for this one, we know that this cloud, the Taurus molecular cloud, is being squeezed between 2 atomic bubbles. What are the stars doing? Well, the YSOs, this is a low mass star forming region. The YSOs don't know anything about this. Most likely because this is a collisional effect. So the YSOs don't feel the effect of the bubbles that are colliding, and star formation happened already a while ago. So this is triggering probably the next generation of stars, but for now is the gas that is being compressed. And we're seeing just the stars that have been formed. Okay, so this is just a pilot test, but now let's go into what we know. So we know that this kind of effect of bubbles squeezing into molecular clouds is very normal in the nearby universe. So we know that that is a tricky neighborhood. So this is the Taurus molecular cloud, but we know that there's many bubbles in this neighborhood, in the nearby universe. So what happens when you look now at the galactic plane, where most of the star formation is happening. So this is the 3D dust density that you get from the 3D dust models. The 3D dust models currently only go to 1.2 kiloparsecs. Some people can push it further from some lines of sight. And this is how you expect the matter to move within those 1.2 kiloparsecs, okay? So this is the way that people have been trying to reconstruct velocities. You just assume circular rotation around the galactic center. If you assume circular rotation around the galactic center, this is what you see in the sky for nearby objects. You see this pattern. Red, going away from you, blue, coming towards you in the second quadrant, going away from you, coming for you, okay? So this is 3D dust, and this is what you expect from the line of sight. So now what happens when we apply that Godzilla matching technique? What happens when we paint the 3D dust with H1 and CO velocities? This is what happens. So we recover the pattern of velocities. So red, red, blue, blue. Overall, most of the matter in the nearby ISM is moving with galactic rotation. So that is not news, but what is cool is that you can actually subtract the galactic rotation and see the effect of the motion in the local ISM and see all of the drift motions that don't correspond to galactic rotation. So I'm not going to show you that today, because this is unpublished, basically because all my collaborators are on vacation, but I'm going to show you a very good example of one expansion that we find. Towards one of the portions of the galactic plane, we find this effect. So this is a mapping, again, remember, distance and velocity. So here is a molecular cloud that is located at between 600 and 1.2 kiloparsecs. So this is the molecular material, and this is the H1 that corresponds to that. So if you see up here, this H1 is moving faster away from us and with respect to this cloud. And this H1 is moving towards us. So what is this motion? This is expansion. This is the best example that we have of expansion in the nearby galaxies and in the nearby molecular clouds. And from these kind of mappings, we are recovering these proper motions. So I have shown you that you can match H1 and CO using the morphology. You can find this offset between the H1 and the CO towards the galactic plane. Maybe they're produced by supernova feedback that can accelerate the more diffuse gas with respect to the dense gas. When you actually put the 3D dust, you can anchor those into distances, and we found evidence of expansion motions of a few kilometers per second. And I think I'm out of time. Thank you.
Do we have questions?
I was just curious about extending it beyond 1.2 kiloparsec using other column density methods for dust, because even the dust 3D uses many methods to get the extinction map. So can one use, for example, Herschel or something like that?
It is tricky because the parallaxes is what gives you the resolution in depth. So it's very tricky. But insofar as the maps improve, or for example, with something like a near infrared Gaia, maybe with Roman, we can have better resolution. And if you saw this and you follow more or less the definition of the projected Rayleigh statistic, the more independent measurements you have of the shape, the higher resolution maps you have, the better is the significance of your results. So right now, we're constrained in two sides. One, from the 3D dust. So if we have more resolved 3D dust, maybe we can do better. Also for some line of sight, we have to push it further. But the other way in which we're limited is in H1. Currently, the best H1 that we have is 40 arc seconds. Hopefully, that's where SKA can help, and we can make high resolution maps of nearby and maybe more distance.
So the resolutions of CO and H1 were identical when you did
in this case, yeah,
yes.
you have to match them. Yeah. But you know that costs a lot.
Any more questions? No?
Adam? Sorry, this may be silly, but so what happens to Taurus in the future?
So Taurus in the future, so what we found is that the H1 doesn't really know about Taurus. So, so the H1 that you would take, if you make some density contours around, is not actually connected to Taurus. All of that H1 is behind Taurus. So Taurus seems to be decoupled from the environment. The H1 is gone, and the CO is being compressed. So most likely it's going to produce another generation of stars. Most likely they're not going to be super high mass because it's only 10 to the 4 solar masses that are being compressed. So looking at the very high densities, there's not much gas. So it's going to make another generation of very low mass stars.
Thanks again. And very good. It's all my fault. Almost there. Oh, update. Well, thanks very much, Jan, and thanks to the organizers for letting me talk about a very different cosmic epoch today, okay? We'll talk about the universe as it was 800 mega years after the Big Bang. That's about 1/18 of today's age, okay? So a little bit of a change. What will be the same as in the previous talks is we are still talking about galaxies, okay? We talk about the interstellar medium in galaxies, and we talk about very high resolution, maybe not as high as Juan was just showing, but 100 parsec imaging at that cosmic epoch. Just as a reminder, we're talking about a universe that is very, very different from today's universe, okay? Just the universe emerging from the dark ages where the first galaxies and stars formed, called the epoch of reionization. So I'm talking about the redshift 6 to 7 range here today. And when I talk about quasars, I really want you to take one thing away or keep with you, that quasars are actually galaxies, okay? They just happen to have a supermassive accreting black hole in the center. And these black holes at this high redshift are actually supermassive, right? They have 1 billion solar masses or more, rivaling the black hole mass that we see locally in the most massive galaxies. So that's quite interesting. And they are thought to live in massive galaxies, and they live in overdensities, and they're very rare on the sky, right? For 25 years now, people have been trying to find these quasars, and there are only 200 known at these very high redshifts. This will hopefully change now with Euclid, where we can push this number much higher and also to higher redshift. And 50 of them are detected with ALMA, and this is what I will be talking about today. So when already ALMA offered a few telescopes, I believe they had 16 at the time for early science, we figured out that we can detect these quasar hosts very efficiently in just a few minutes of integration time, both in the dust continuum and also in the C+ line. And that immediately tells you that, of course, you can push this to higher and higher resolution, which we did over the years. So I don't want to bore you with all the details here, but we successfully tried to get higher and higher resolution, a few kiloparsec resolution, and you see here some quasars. The left panel is always the continuum, and the right panel is always the C+ line. And of course, you see that these are, sometimes we're talking 100 sigma detections here, right? Which means that with ALMA using more and more extended configurations, you can actually start to resolve this on a few 100 parsec scales, which is exactly what we did. Now, only later came the simulations that we can now compare to. And there's actually one very interesting thing here that I would like you to take away, and that is, this is the same galaxy. This is actually C+ snapshots, separated by only 100 mega years in time, okay, at this very high redshift. This corresponds to delta Z of about 0.5. And you see that these galaxies, or the same galaxy, looks completely different, right, 100 mega years later. This is very different, of course, to the local universe, right? If you look at galaxy now, and you look at the same galaxy 100 mega years later, yes, it may have rotated by 180 degrees or so, but to first order, the structure will be the same. This is not what's happening here. Things happen very, very, very fast in the early universe. And of course, there is not a zero onset for galaxy formation, right? So if we have a redshift 6 galaxy and a redshift 6.5 galaxy, it's really quite difficult to interpret this. Also, if we have AGN feedback in these galaxies, the simulation shows that we can only trace that feedback over very short periods of time, only 10 mega years or so, right? You see here's there's no AGN activity, then the quasar turns on. You see a cavity, but then another 10 million years later or so, that cavity is gone again. So trying to catch that feedback is actually really complicated. These are just some simulations of how ALMA would look at this and the C+ emission if you had 20 hours of integration time. Okay, now let's start with showing some actual data. So the ALMA data that I will show you today comprise of almost 200 hours or so, pushing ALMA really to the limit and to the most extended configurations. One thing we also wanted to look after in the images that I will show you is the potential signature of a central black hole. I told you that these are accreting supermassive black holes. This is in fact how they are selected from the sky, right? Through the very bright UV emission. So you would expect that they also show up some kinematic signature in the center, as of course we see in local galaxies quite prominently, which gives you a separate handle on the black hole masses, which currently for these high redshift quasars, we're using scaling relations based on local scaling relations, mostly UV lines, of course now with Webb, also the H alpha line. But there's some extrapolations here. It would be very nice to get a kinematic measurement, for example, like Martin is doing in the local universe. Okay, now let's move on to the observations. I will just highlight a few of these now. This slide you have seen earlier. I will now look at this galaxy here, which is actually the first quasar where we really tried to push the resolution as high as we could. So this is now 400 parsec imaging of this quasar at redshift 6.6. That's about 800 megayears after the Big Bang. The dust continuum, the C+, the velocity field, and the velocity dispersion. Right, if you look at the velocity field, is it just a big mess? Okay, I will show you some channel maps in a second. There's very high dispersion throughout the galaxy. We see this in most of the objects of order 100 kilometers per second here, which means that they have really puffed up disks. Okay, these are not galaxies as we see them in the local universe. So also we could not really find the kinematic impact of the central supermassive black hole, which is situated here with the cross. So all the central locations of the supermassive black holes come from Gaia corrected positions. Okay, so if we look now at the channel maps, I'm a huge fan of channel maps. These are the C+ channel maps. You see that there's indeed a very chaotic thing happening here. And this we published actually quite a few years before the simulation that I showed you in the earlier slide, right? If you now look at this channel map here and this simulation here, it's kind of intriguing, right? Maybe we do actually see some feedback by the central quasar. Even the color scale is the same. This is another one, very compact mission, very, very bright, also with ALMA. Again, the continuum, C+ line, velocity field, and the dispersion. Here you see the velocity field is really like a disk-like structure, right? Very regular, actually. The velocity dispersion, again, is very, very high. So when you look at the actual mass that is enclosed as a function of galactocentric radii, you have the central supermassive black hole, a few billion solar masses, but then you also see that the gas mass is actually very high already in the very center, right? So of order 2 times 10 to the 10 solar mass of gas is sitting in this host galaxy, and a few times 10 to the 9 just in the central pixel. We have a resolution of 200 parsecs here, okay? So that actually is more than the supermassive black hole in the center. So there's no way we can actually see it kinematically, which is kind of a bummer, right? So once the gas concentrations are too high, we just cannot see the black hole, even if it was there. So that was not great. Of course, you only know in after the fact. You need to look first and then see what the gas is distributed like. This is actually a slide I put in this morning because I always wanted to put in that slide and I never did for many, many years. This is on the same scale showing this quasar and everybody's favorite galaxy M51, okay? And you can now see that we have very similar spatial resolutions. The reason why we don't see so much, oops, sorry, that was the wrong key. So much structure here is that, on these scales, there's also not so much structure in M51, right? 2 minutes, very good. So, but you can see that, the total gas mass in M51 is 6 times 10 to the 9, and the gas mass here is 2 times 10 to the 10. Very, very extreme, very different environments. Okay, another one, where we have a beautiful bar kind of like structure, certainly some tilted structure in the velocity field. Interestingly, right, this galaxy sits in a very massive Lyman alpha halo, right, as traced by the Muse imager of the DLT. And if you compare the kinematics of the C plus in the center and the Lyman alpha around it, there seems to be some offset here, right? So what that means, I don't know. But it could be that there could be, you know, if gas falls down, there could be a torque that is then providing this tilt here that we see in the velocity field. But, you know, the thing I just wanted to keep in mind is that we can now do at redshift 6.5 or so, very similar studies to what people have been doing in the local universe, you know, with, you know, warp models, et cetera, et cetera. The warps in the local universe maybe come from mostly interactions with other galaxies. Here, it may also be interactions with the circumgalactic medium. All right, and we can, you know, extend the star formation law to much higher densities now because we trace densities that cannot be probed in nearby starburst galaxies or even nearby ULERGs, just because things are so compact and so small. All right, moving on. I have one more. This was our best case to actually detect the kinematic signature of the central supermassive black hole because we knew that there's not so much gas in this object. So we thought then we can go to the center and see the kinematic impact. What you can immediately see here is that dispersion is again very high overall, but we don't see a central peak. Only after the fact, then we did the Gaia correction and found out that the black hole may actually be sitting away from the gas, which is kind of unfortunate. So we don't know what that means, right? So it could be either that we are overestimating the mass of the supermassive black hole in this particular system, or there is some issue and the black hole is actually not where we think it is. Okay, so 100 parsecs. So now we're pushing this further. I've already shown you this galaxy earlier. We're now going to 100 parsec resolution. And interestingly, we lose sort of the emission in the C+, while it's still very bright in the continuum. We did lots of analysis, you know, with playing imaging, removing baselines in the UV plane. But the first order, right, the continuum is very, very compact. The C+ is more diffuse, and we can sort of rule out C+ emission on scales larger than 200 parsecs. And I will stop here. I want to keep you, please remind yourself that, we're talking a very different universe. Galaxies look very different. Things happen very fast at these early times, so we really need large samples to basically get good snapshots. And we still haven't seen kinematic evidence of the supermassive black holes. I will stop here.
There. Hi, great data, Fabian. In your simulation that you showed where you see the peak in the velocity dispersion, is this due to true turbulence in your model, or is it just the beam smearing of the steep gradient in the inner parts?
Okay, let me go back to that because I'm not sure I 100% understand your question. So you mean at the very beginning where I showed the effect of the central supermassive black hole? Yeah, so this is, let me now think. Okay, so I mean, as you can see here, right? Oops, sorry. This effect here is just from the beam smearing, right? And then if you add an extra central point source, this is what you get. I'm not sure I'm answering your question.
So is this beam smearing of the steep gradient of the rotation in the middle, or in your model do you have true turbulence?
No, this is just very simple. Yeah. No, there's no turbulence here. Sorry. Yeah.
One last question before the break. Yes, Florida.
Thank you for that talk. I have two questions. One very basic. How do you know these are quasars?
Well, so quasars are they're just selected based on the accretion disk that we see in the rest frame UV, right? So you look at the spectrum and you very clearly see all the lines you would expect, Lyman alpha, magnesium 2, C4, broad line region, right? So that's how you select them.
And what are the chances then that you are not seeing the gas because you're ionizing your gas? These are very strong quasars, right?
So that was actually the first huge surprise, right? That we actually do see the gas. I mean, we actually, all the way to the very center, right? We see all the cold dust in the C+.
Absent. Your C+ in your last example was absent.
Okay, okay, let me go to that real quick. I still have 10 seconds. I'm just making this up. This says 0. Okay, so this is the one you're talking about, right? I mean, it turns out that there is actually C+ all over the place, right?
In that place where it's not, I'm assuming that's where the AGN is.
I mean, that was the image I showed you earlier. I can show you more slides offline, but where we had the lower resolution images, this cavity, right? Which is sort of indicative of maybe some quasar feedback. But thanks very much.
Let's thank all our speakers again. All right, enjoy coffee. Great. Yeah.
Oh, okay. Oh,
Do
very
they
good.
give me a timer up here? I guess they do.
It doesn't work, I think.
Oh,
so.
okay. But it's not always accurate. Will you do 5 minutes? or-
Oh, sure. Also, can you put the slide for the first speaker already? It's about 1 minute before. Okay. So why don't we just start? Hello? It's still on? Okay, it's less than 1 minute before the session starts, so I'll be chairing the next session. And for speakers, I'll give you either 5 minutes warning before the talk ends or 3 minutes before the talk ends, depending on if you're a reviewer or contributed talk. And I guess it's about the time, so why don't we just start? The first speaker is Karin Sandstrom, and she'll talk about the relationship between coal dust and gas. Please.
All right. Well, thanks everybody. Welcome back from the coffee break. Thank you to the organizers for giving me the opportunity to talk about the very best part of the atomic and molecular ISM, which is the dust. All right. So there's a lot to talk about here. So I've narrowed it down to about 3 things I'd like to discuss. The first of those is, what do we know about the dust to gas ratio and how it varies? This is a topic that's already come up a couple of times already today, and I'm sure it will come up even more later on. After that, I'd like to switch to saying, okay, maybe we understand a good amount about the dust to gas ratio, which you may debate after you see what I present. But if we think we understand it, maybe we can turn things around and use dust as a tracer of gas. And what do we learn? There are more difficult things to trace and understand and calibrate, such as the CO to H2 conversion factor. So we may use dust in order to try to understand that. And then lastly, we will dig in on this question a little bit that we've heard from a couple of speakers today about whether mid-infrared emission, which we can observe with extremely high resolution now with JWST, lets us also trace gas. So to get started, if we're thinking about measuring dust to gas ratios, we need some sort of dust tracer. Generally, this will be maybe the far infrared emission. If we understand something about the dust temperature, we can turn that measurement of the far infrared emission into a dust column density or dust surface density. But there are other options. We will also need our gas tracers. So we'll have CO to trace H2, and then we'll have our 21 centimeter. So this is an inherently multi-wavelength set of observations that we need in order to understand the dust to gas ratio. And you'll note that in there, we also need to understand the CO to H2 conversion factor. So these things are inextricably linked. Our knowledge of what the CO to H2 conversion factor is based on a lot of information that we think we know about dust. There are some other ways to get at it in a few circumstances, but this is the main one. So if we were to convince ourselves, though, that we knew a lot about the dust to gas ratio, we might be tempted to instead do this, where we think that the CO to H2 conversion factor might vary a lot more than the dust to gas ratio or the dust to metals ratio, so we can pin our knowledge to something else and use that to figure out something about the CO to H2 conversion factor. Whether or not that's a good idea, there's still, I think we've done a lot of it, and there are circumstances where this works really well. There are also a lot of circumstances, I'd argue, where we don't have a huge understanding of what's happening with the dust to gas ratio. So let's talk about those first. So the current state of things, I would say, is when you go to try to measure the dust to gas ratio in integrated measurements of galaxies, the thing you will find is that to first order, it varies with metallicity. And this is very understandable because dust is metals. So if we started off with a baseline assumption of a fixed fraction of the heavy elements in the form of dust, we would see a linear dependence of dust to gas ratio on metallicity. This is not exactly what's observed. People tend to find that this steepens at low metallicity so that you have even less of your heavy elements in dust as you go to lower metallicity. So this is a nonlinear variation. You can also state this as the dust to metals ratio is changing. The other thing that's interesting, I think, from this plot and others like it that try to do integrated measurements of dust to gas ratios, there tends to actually be quite a bit of scatter. And it's not 100% obvious, whether that is because you're trying to represent an entire galaxy with potentially a gradient of metallicity, a gradient of where all the gas and dust is with one particular metallicity and dust to gas ratio, or if some of this is real variation in the dust to gas ratio. So there is another way to get at this, and this is something that people have been looking into a lot recently, which is using depletion measurements to measure dust to gas ratios. So depletions are measured using UV absorption lines or optical absorption lines of various elements. If you can figure out what the baseline amount of metals is, you can see what's missing from the gas that is in dust grains and use that kind of, it's a direct way to measure something about the dust to metals ratio. The tricky parts are that you have to assume various abundance patterns. You often only have a small subset of elements where you have some measured depletion. But there is a large compilation here from the review article of Perot and Hauk showing the measurements of damped Lyman alpha systems out to high redshift with dust to gas ratios and dust to metals measured from depletions. So one of the tricky things, though, is that the most recent work on this is showing a tension between what you find when you look at nearby galaxies and do this measurement with far infrared, CO, and H1, and what you find when you try to compare to the results from damped Lyman alpha systems. So this is a compilation from Roman Duval et al. In 2022. This is the metal survey, which measured depletions in the large and small Magellanic Cloud as an attempt to bridge this gap between what you can do in more distant absorption line systems and also measure things with the far infrared CO and H1 approach. And what they tend to see is that the depletion measurements give you a much less scatter, much more linear kind of behavior in the dust to gas ratio as a function of metallicity. Some of the differences that can come about here, and they're not small, have to do with how you interpret a given abundance ratio in order to turn that into a dust to gas ratio. So this is using a prescription from Dacia et al. 2016. If you instead try to tie this to what was observed in the Magellanic Clouds, you can move around the DLA points quite a bit. So there's still a lot of uncertainty in the difference between what you're learning from the far infrared and what you're learning from depletions. Another interesting effect may be that the depletion measurements are lines of sight, pencil beams through the ISM, even looking at the Magellanic Clouds, whereas the far infrared measurements are, at least the ones shown here, tend to be over large scales within galaxies, averaging together a lot of ISM. So these differences may be related to whether or not what you're capturing with your pencil beam versus a large kiloparsec scale region. So if we then try to understand how the dust to metals and dust to gas ratio might vary at a fixed metallicity. So if we go in a galaxy and pick out just one constant metallicity at a given radius, we can ask how does dust to metals depend on environment? And this is a compilation from Milky Way measurements. So from the Jenkins kind of classic 2009 paper, you can predict that the depletions change as the ISM gets more dense. So you have more of your heavy elements in dust at high densities. And so you would expect a small variation in the dust to gas ratio. And that's what's observed in the Milky Way. So over here, you can see as a function of H1 column density, a change in the dust to gas ratio. So this is relatively small. You'll notice this is not a huge change in the dust to gas ratio. If you try to do this in the Magellanic Clouds, you actually see something a bit more dramatic. So there's some evidence from depletion measurements and for very high resolution far infrared H1CO type measurements that there's more of a change in the dust to gas ratio with H1 column density in the Magellanic Clouds. And you'll also notice that based on this, there's actually factor of 2 or maybe slightly more discrepancy between the amount of dust you would get from the far infrared and what you get from depletions. So this is a puzzle still. There's a lot to be learned yet. One important fact, of course, is the Magellanic Clouds are interacting. And we saw some beautiful images this morning with all the H1 spread everywhere around there. So it's really complicated to actually isolate which lines of sight are purely H1 associated with the dust and which aren't. There's been some really interesting work kind of comparing dust and H1, a little bit like what Juan showed us earlier, trying to associate these kinematically by Claire Murray. So I think there's a lot to be learned still in the Magellanic Clouds, but I'm gonna zoom out now to kiloparsec resolution, where because of averaging everything together, things actually get quite a bit better. So this is some work from my PhD student, former PhD student, Yi-Da Cheng, who's now a postdoc at AJA. And he measured the dust to metals ratio in a series of galaxies where we have really nice metallicity measurements from auroral line calibrations. And what he found, which was sensitive to the conversion factor, which makes it a nice handle for later on trying to reverse this and figure out something about the conversion factor, is that at kiloparsec scale, we did not see a huge variation in the dust to metals in these galaxies. So it was around 0.5 plus or minus 0.1 or so throughout these galaxies. And this is nice because if we understand this value at some level, we might then be able to turn it around and use fixed dust to metals or something about the dust to gas ratio to let us learn about the conversion factor, which we think might vary a lot more. I'll note that when you look at the dust to metals resolved in nearby galaxies, for instance, M101 here, the primary trend, which you can see as a function of H2 fraction here, is radial. So there's a large variation radially, especially in M101, which has a huge metallicity gradient. If you try to remove that trend and see if there's any residual correlation between the dust to metals ratio and any parameters describing the local environment, it's pretty weak. There's maybe a trend, a pretty weak trend, to have higher dust to metals at higher H2 fractions. So this would agree with the picture where you're having dust grow via accretion in denser parts of the interstellar medium. So I want to briefly summarize the dust to metals, dust to gas part of this. So we can clearly see it varies with metallicity. That makes a ton of sense. It is, however, most likely steeper than linear. And so therefore the dust to metals ratio changes with metallicity. There is some unexplained discrepancies still between what you get from absorption lines, so depletion measurements, and what you get from far infrared H1CO type measurements. This may be related to the dust optical properties, which we don't actually know a huge amount about in a lot of extragalactic circumstances. So this is a likely scenario for where that may play a role. Resolved within the galaxies, though, what we can see is that dust to metals, so the fraction of your heavy elements that are in dust, is relatively constant. And so do we know enough to use dust as our tracer of gas? I think we do. We can argue about it in the discussion if you'd like. So that's what I'm going to do next. But before that, I just want to point out that one thing that's happening now, which I think is really exciting, which is going to help us understand this a lot, is the fact that people have now implemented live dust models in galaxy simulations. So this means not just a fixed dust to gas ratio, it's actually dust that is evolving along with the galaxy. And these are now in cosmological simulations. Caleb Choban did this with the fire simulations. And so we can track the input of dust, the growth of dust via accretion, dust destruction throughout these galaxies. Okay, so in the next part, I want to flip it around and argue that we learn a lot about the conversion factor using dust as a tracer. And the basic point here is that although dust to metals may vary, although dust to gas can change, it changes less than the conversion factor does. So we can try to use this as our handle and understand something about how the CO to H2 conversion factor varies. We know quite a bit about this at this point. So it's well known that there's a very strong metallicity dependence in the conversion factor, probably due to the envelopes of CO dark H2. And this has now been observed using a variety of techniques. And there's general agreement that the conversion factor quite steeply increases as you get to lower metallicity. There's also trends having to do with CO excitation. So this is from recent simulations that have high resolution and include realistic chemistry for CO. and its excitation that let you track what you expect to see for the CO to H2 conversion factor. And this reveals trends that go in the direction you might expect. As the CO is more highly excited and the gas is warmer, you can get more CO emission from that. And that decreases the CO to H2 conversion factor. For measurements using dust in other galaxies, we can see that in the centers of galaxies, the conversion factor tends to get lower. So something I worked on for a while. This is a plot from a paper a long time ago now. We also know that in the Milky Way's center, and this you can measure with gamma rays, so completely different way, you also see low conversion factors. And while there is quite a bit of uncertainty further out in the disk in this analysis, it is uniformly the case that the center of the Milky Way shows a low conversion factor, just like what we see in other galaxies. So this has been updated and done much better in recent years by Jakob den Broek, who looked at multiple CO lines, much nicer data sets, and has used dust as a tracer of gas and found this sharp decrease again. This is M101 in the centers of some galaxies. You can see this showing up now in both multiple CO lines. So recent work by Ida Chang, who I already mentioned, a postdoc at IAU GA, used an assumption of a fixed dust to metals ratio along with measurements of dust, CO, H1, and metallicity, which you need to implement the use of this fixed dust to metals as a constraint. He used this data set to measure resolved maps of alpha CO in 37 different galaxies. And this is a compilation of how those measurements vary with local environment. So you can see that it's correlated with a lot of different parameters. Alpha CO tends to be low, again, in the centers of galaxies. It tends to be low in places with high interstellar radiation fields. It's dependent on metallicity. Excuse me, recovering from being sick last week, so my throat's a little messed up. And you can see a lot of different trends here that likely encompass variations that have to do with CO dark gas, excitation, and emissivity effects. So this is a really nice compilation. There are not that many galaxies where we have both far infrared emission and all of the relevant atomic and molecular gas data and metallicities to do this. So getting more of those and higher resolution is a really exciting prospect. I'll just note that we heard from Eltha Teng earlier today that these dust-based measurements match up quite well with what you get from another very limited resource, which is multi-line CO isotopolog modeling, where you can try to measure the properties of the molecular gas and the CO to H2 conversion factor using models that predict 13 CO, 3 to 2, 2 to 1, 1 to 0, 12 CO, all of these lines. So this is very reassuring. And it also lets us get the understanding that CO opacity is playing an important role in a lot of these circumstances for setting the conversion factor. So putting this all together, Ava Schinner and Adam Leroy have a recent review article where they've combined kind of the current best knowledge of each of these terms of the variation in the CO to H2 conversion factor, including the CO dark gas part, the emissivity that may be related to the opacity of CO, potentially due to the weight of the ISM compressing molecular clouds in centers of galaxies where there's a lot of stellar mass surface density. And it also includes the variation of the excitation and temperature of the gas. So if you're looking for the best current conversion factor prescription that doesn't rely on the velocity dispersion, you can try Elthas for the velocity dispersion, and this one if you have stellar mass surface density, star formation rate surface density, and other properties of the galaxies. So just to note, though, that our limitation on what we can do with far infrared is set by the fact that Herschel, at the wavelengths we need in order to measure dust masses, has a resolution of 18 arcseconds. So that's what that looks like in NGC 628. 18 arcseconds gets you past the peak of the SED, where you can hope to do a good job at measuring the total dust mass by modeling the far infrared SED. But this is a big limitation. I will note that if you're interested in 18 arcsecond resolution maps of dust mass, there's a paper we recently submitted, Chastanet et al. 2024, where we have 800 local galaxies, all of the galaxies with Herschel plus WISE observations, where we've done the dust modeling, and this will all be available at URSA after the paper is accepted. So if you need dust maps of nearby galaxies, this is your place. I mean, obviously, everyone has their own dust modeling techniques, but this one's pretty good, I think. So how do we do this if we want to get higher resolution, though? If we don't want to be limited by 18 arcseconds? And that is where the mid-infrared comes in. So with JWST, we now have access to ridiculously high resolution, very sensitive mid-infrared imaging of nearby galaxies. And this is tracing dust emission, and we might hope that this is something we could use to map out the distribution of gas at much higher resolution than what we've been able to do before. So JWST has this beautiful set of mid-infrared filters that cover emission features from polycyclic aromatic hydrocarbons, which are a great tracer of the mid-infrared dust emission. And if we are looking at this mid-infrared emission, it is from, sorry, this still has 4 minutes on it. This has stochastically, what's that?
That's for the end session.
Okay, sorry. This is from stochastically heated dust that in the mid-infrared, if you are looking at this part of the spectrum, it is linearly proportional to the radiation field strength. So if we think about what the mid-infrared should contain, it should be something proportional to the amount of the mass of PAWs relative to gas and the radiation field intensity, and then the gas surface density. So if the PAW to gas ratio is approximately constant and U is relatively constant, then we might expect this to be a good linear gas tracer. So I'm just going to jump ahead to say that it does actually appear that this works quite well. So there's a relatively linear correlation between gas as traced by CO in the H2 dominated parts of galaxies and mid-infrared emission. So this may indicate that we have a relatively constant radiation field intensity in the diffuse ISM. And this gives you the possibility of potentially having a gas tracer that gets you 10 parsec resolution, extremely high sensitivity, particularly if you can extrapolate from the H2 dominated parts into the H1 dominated parts of galaxies. So apologies for the little misestimate of the time there, but I will leave you with my conclusions. I think there's a lot of exciting things to learn. We have some good ideas about how the dust to gas ratio is working, the CO to H2 conversion factor, and we may be able to use mid-infrared emission as our really high resolution tracer of gas over the next 15 years of JWST observations. So, thank you.
Thank you very much. Any questions? Over there? Oh, so there's a microphone.
Hello, thank you for your talk. I was wondering if you think the discrepancy between the emission and dust depletion could be because we might be probing different types of dust?
In different galaxies? Or what do you mean?
Like comparing emission to dust depletion.
Yes, so I mean, it's a very different measurement. You're measuring the same dust population. It's just a really different way to look at it. So there's, in the far infrared part, for sure, there's a big uncertainty about what the properties of the dust are that give you that, the infrared opacity you need to use to interpret it. We have that pinned in the Milky Way to a lot of different measurements, but what it is in other galaxies is not, I think, as barely known at all, maybe, let's say it like that. But the other thing is that the interpretation of the depletion patterns, so for a lot of these DLAs, you don't know the starting metallicity, so you have to infer both the depletion pattern and kind of the overall chemical abundances in the galaxy from a few absorption line measurements. So both of those processes are pretty uncertain.
Thank you.
We could take another quick question, but please change the slides to the next speaker. Oh, there. There's a microphone.
Thanks, Karin, for the very nice talk. So the last point about the correlation between mid-infrared and CO, I might have missed it. On which scale are you looking at this? And so does this mean that there is a one-to-one match every time between pH's emission and CO?
So the scale is 10 to 50 parsecs or so. And I mean, it's very close. If we heard a really nice talk about radiation field intensity earlier today. So we see exactly the same thing, right? Where you go towards a source, like an H2 region, a young star cluster, and things become very nonlinear there because the radiation field intensity is much higher. But if you get away from that into the diffuse ISM, things seem to work quite well.
Thank you.
All right, thank you very much. Let's move on to the next speaker. So the next talk will be given by Chloe Bosenworth, and she'll talk about resolved dust emission and CO stop logs in giant molecular clouds of the Andromeda galaxy. So please go ahead.
Hi everyone, I'm Chloe Bosenworth. I'm a PhD student from the University of Hertfordshire, and thanks to the organisers for the opportunity to give my talk today. I'm going to be presenting results from an SMA survey where we obtain resolved dust emission and CO in individual GMCs of the Andromeda galaxy, also known as M31. So I'm lucky that we have had nice introductions to dust and CO as traces of molecular gas. So in local and Milky Way observations, dust has been shown to display the ground truth, but we're primarily limited for resolved dust detections to the local galaxy. That is until the recent SMA wideband sensitivity upgrade, where we've been able to obtain resolved dust emission in individual GMCs in an external large disk galaxy, M31. So we have now completed a large-scale science program with the SMA over 4 observing seasons, obtaining simultaneously dust continuum emission and free CO isotopologs with identical UV coverage and astrometry. We use the SMA in the subcompact configuration and the 230 gigahertz receiver. So the combination of the SMA and M31 is perfect for observing dust emission in individual GMCs because we can reach as small as 15 parsec resolution. And so I'm now presenting the results from our full survey, but we already have 2 papers presenting results from the first 2 observing runs. So quickly to introduce everyone to M31, like the Milky Way, it's a bad spiral galaxy, and it's our most nearby large disk galaxy. I show here the Spitzer infrared image. It nicely shows its structure. Now I want to briefly touch on our methodology. So I show here an example of one of our dust continuum maps. I'm able to overplot also the 12 CO contour and a 13 CO contour, as well as the dust emission contours at different signal to noise thresholds. Previously, we used a signal to noise threshold of 3 sigma for our final sample. Here, we have reduced this to 2.5 sigma. I experimented with varying with how low we could go and using the 12 CO contour as a guide of where to look for dust emission from the GMCs. Another requirement for our final sample was that from the spectral cubes, which have velocity information on the CO, we want to see a single Gaussian spectrum. This is to avoid line of sight contamination from multiple clouds, because as we know, M31 is highly inclined. So our final sample size is 46, increased from 32, and we increased the number of resolved sources from 10 to 21. We measure dust mass and CO luminosity both within the 2.5 sigma dust masks, and we calculate these as shown here. So the ratio of these gives so we've had nice introductions to alpha CO, the CO to cloud mass conversion factor. I here present CO to dust mass conversion factor called alpha prime of CO, which is the ratio of dust mass to LCO. And it's converted to the traditional alpha CO once you use the gas to dust ratio, which can be done in various ways. So applying our methodology, we obtain an alpha prime using the 12 CO luminosity and 13 CO luminosities for our individual dust detections from the GMCs. On the left, it's using 12 CO luminosity. On the right, 13 CO luminosity. Along the top is our resolved detections. Along the bottom, unresolved sources. The differences in between the resolved and unresolved sources is negligible with, like, compared to the standard deviation scatter, and our mean values calculated are in agreement with our previous values. So how does this compare to a Milky Way value? So within uncertainty, if we are to assume a gas to dust ratio that is typical of the Milky Way, of course, you may not want to assume it this way, this can be done in various ways, but if we assume this, we find an alpha CO value, which is compatible with the Milky Way value using 12 CO. So I want to briefly highlight another survey I've been part of, which is optical spectroscopy with the MMT towards H2 regions, individual H2 regions in M31. And a subset of 30 of these H2 regions are associated with SMA observed GMCs that made it into our final sample. Therefore, I've been able to plot there. So on the left is alpha prime using 12 CO. On the x-axis, it's oxygen abundance from the optical spectra. And the primary metallicity range probed here is 8.5 and above. We actually found a constant alpha prime CO for this, but of course we expect to see significant dependence, especially at low metallicities. So it's very important for future work to cover this range. And also the gas to dust ratio will depend on metallicity, and we haven't applied this yet to the result. So the last result I want to highlight that we can get by comparing CO and dust from the same GMCs is, are these dust emitting regions of the GMCs bound and or virialized? So when the gravitational potential energy and the kinetic energy are equal, a system is bound. Virial theorem states, as you see here, and we investigate this comparing virial mass and luminous mass, and virial mass is calculated as shown here. Already published are results for the CO clouds in general. So from the same set of observations as I'm discussing here for the dust. So in Ladder et al., they showed that the GMCs, which are traced by 12 CO because of the extremely long observation times needed to resolve the dust, the 12 CO traces the entire GMCs. We find that these are primarily unbound. But when you go to the higher column density material, which 13 CO traces, these are primarily bound. So we're interested now in what we see for the individual dust cores. So we found, again, these are primarily bound, and not only that, but close to being virialized. Even the sources which lie in the unbound region, they're close to being, within 2 sigma at the most, they would be classified as bound. So we used 13 CO line widths for this because we find it's better spatially matched in our observations to dust. We also expected to see this evidence that dust is tracing dense gas because from NOEMA observations presented in Forbridge et al. 2023, HCN was well spatially matched with dust. So I went faster than I expected there, so I'll run through my conclusions. So the SMA has been able to obtain resolved dust detections outside of the Milky Way and the Magellanic Clouds in the Andromeda Galaxy. So we look forward to future upgrades and telescopes in radio astronomy that to be even more sensitive to dust. So it's very important I emphasize that if we assume the gas to dust ratio typical of the Milky Way for M31, alpha of 12 CO is compatible. From the metallicity range, which we probed in M31, we saw no apparent dependence of alpha prime CO on metallicity. So assuming a simple galactocentric radius trend like a metallicity gradient shows, this is not necessary, at least for M31. We found that 74% of our dust cores are gravitationally bound. So this confirms and indicates we are indeed tracing the dense material, similar to how we do in 13 CO and HCN, which dust is spatially well matched with. And with that, thank you for listening, and I welcome comments and questions.
Thank you very much. Any question?
So do you see any relationship between the CO to dust ratio and say the presence of the nearby H2 regions that you're getting metallicity from? Like, is there any evidence of heating affecting the dust?
Yeah, so that's actually one of the first things we looked into, because as well as the optical spectra, we have a VLA survey, which has like an even larger H alpha sample, like detection sample. And we thought, I'm assuming we link this to the dust temperature assumption. So if that's, hopefully that's relevant to your question, then that's one of the first things we checked is, could this be affecting it? And in detail in Bien et al. 2021, he did this experiment. But what I've done is, for the outliers in my plot, but for the individual alpha prime CO values, what dust temperature is needed to bring the outliers down to average. And you would need to assume a dust temperature instead of 20 of something like 48. So that the dust temperature assumption can account for the whole discrepancy, is what I found. I hope that answered.
Oh yeah, but for online speakers.
Okay. What about the orientation? Of course, when you see in this direction or that direction, have you included that one, or is it averaging from certain sample?
You mean like the inclination of the galaxy?
Yes, exactly.
Yes, so one thing which I mentioned, we take into account that we only see a single Gaussian from a spectral cube extracted within the dust mask, so that we are highly likely to not be looking at multiple clouds at once along the line of sight, because that can be caused by a high inclination. Another thing, this is referring again to the outliers in the alpha prime of CO plot. There could be the case where the dust and the 12 CO are not quite matched, and this is highly likely a line of sight effect, or it could be part of it. So it can lie at the edge of, so it lies where we get a weaker 12 CO detection than say the center of the GMC. It lies more at the edge of the GMC.
Okay, is there one more?
Do you know if these lie inside the extinction map covered by the HST survey? Happy to chat offline, but it'd be a chance to compare
Yeah,
also.
I think I would want to confirm my answers.
Totally.
So yeah, thank you.
Is there any other question? If not, then let's thank Chloe again. Okay, so the next speaker is. Oh, I guess we should wait for the slide. The next speaker is Alice Comcast, and she will talk about the molecular gas and dust extinction ration revealed by AlmaQuest. Please take it away.
Thank you. Hi, everybody. I'm Alice Comcast. I'm an ISO fellow. And let me check here how to change my slides. Okay, yes. So today I'm talking about the connection between the molecular gas and dust extinction revealed by AlmaQuest. So, oops. Yeah. Okay, so I think that in this focus meeting, we all appreciate the fact that the molecular gas mass is important. We know that in order to estimate the molecular gas in galaxies, we can use different tracers, CO transitions, atomic, ionized carbon. Also, we saw that we can use dust in emission. But we all know that all these tracers are really time consuming. So in order to have an information about the molecular gas mass on these tracers, we need a lot of telescope time. This is why in this talk, I want to talk with you about the use of the dust in absorption, in particular the dust extinction from the Balmer decrement, in order to overcome this problem. And so in this way, I will show you that we can estimate the molecular gas mass for large samples of galaxies, or also a lot of spatially resolved data. So a few years ago, we found that the global molecular gas of galaxies correlates with the Balmer decrement. In particular, we did that with using 500 galaxies selected by the X-cold gas sample. They are quite massive galaxies for which we have global information about the molecular gas mass from the CO luminosity from NOEMA, and the dust extinction from the Balmer decrement, so the ratio between the H alpha and H beta from the SDSS spectroscopy. As you can see from the plot, there is a clear connection between this global CO luminosity, that is a proxy of the molecular gas mass, and the Balmer decrement, that is a tracer of the dust. And you see that the correlation exists for the star-forming galaxies that are the blue points, but then there is a huge scatter if we include galaxies with a certain AGN contribution. So here is the same relation, but now I'm translating the CO luminosity into the global molecular gas mass using alpha CO conversion factor. And of course, you see the same relation. Here I'm just showing the fact that for face-on galaxies, the correlation is steeper. And this is basically due to the fact that the majority of the dust in galaxies is located into the disk of galaxies. And so the optical light, a fixed molecular mass, it's more absorbed along the disk of galaxies. So the correlation, global correlation exists. And I want just to tell you that we can apply such relation in order to estimate the molecular gas mass for a statistical sample of galaxies. We did that a couple of years ago using 150K SDSS star-forming galaxies. We used the Balmer decrement to estimate the molecular gas mass. And we estimated, as an example, the star formation efficiency, that is the ratio between star formation rate and molecular gas mass, that you can see in the right plot. And basically, we color code our galaxies and we plot them in the star formation rate stellar mass plane, finding that the star formation efficiency seems to be constant along the so-called main sequence of star-forming galaxies. We also quantified the gas fraction that you can see in the left panel. And basically, we found that the main sequence shape, or the so-called bending at high stellar masses, can be driven by a lower gas fraction. This is just an example of an application. But now let me move to the real topic of my talk, that is showing that such a correlation exists also on a kiloparsec scale. In order to do that, I use the ALMA-QuEST survey. ALMA-QuEST stands for Alma Manga Quenching Star Formation Survey. The PIs are Lin-Wei Lin and Sarah Ellison. And ALMA-QuEST consists on 47 local galaxies from the manga, for which we have the optical IFU, as of the Balmer decrement, plus 4 ALMA programs in which we detect the CO120 at the same spatial resolution of the manga galaxies. This is the ALMA-QuEST distribution in the star formation rate stellar mass plane. As you can see, the ALMA-QuEST galaxies are quite massive. They are located on, above, and below the main sequence. And during this talk, I will use the optical properties taken from the PIPE 3D collaboration. So of course, we select only spaxels with certain characteristic, only star-forming spaxels, and with a certain signal to noise on the emission lines. And we select only galaxies that are face-on in order to avoid the inclination effect. We end up with more than 10K spaxels, and we have so a good statistic. This is the result. So we found that on a kiloparsec scale, there is a relation between the CO intensity or the CO luminosity and the Balmer decrement, as you can see from this plot. The correlation in this case is moderate because you can see the Pearson and Sperman correlation coefficients in the plot. Of course, if we use a constant alpha CO conversion factor, we have the same relation. And we can also parameterize the relation in order to apply it in other works. We can also study the variation of the relation with the with different physical properties of the spaxels. In particular, we study the variation of the relation with the gas phase metallicity. And here, so you see the same correlation, but color-coded according with the metallicity. As you can see, the fixed sigma gas, the metallicity decreases with the Balmer decrement. A fixed Balmer decrement, the metallicity increases with the sigma H2. Such relations disappears if we assume an alpha CO conversion factor that depends on the metallicity. And here I'm showing just an example, taking the alpha CO from Israel and collaborators 2000, where you can see that the relation is with less scatter And so with higher correlation factor, this kind of interesting to me. I would like to talk with you, then in particular with Karin, in order to understand the relation of the connection, the relation with the alpha CO conversion factor and the metallicity. Then we also compare our results with the previous results. In particular, in order to do that, we convert the Balmer decrement in the optical extinction using simple assumption. And basically, we compare with results from the Edge Khalifa survey published by Barrera Ballesteros in 2000. And here you see the results for Spaxel with a similar spatial resolution. You see that they observe a sort of scatter plot. There is not a clear linear relation as we observe in AlmaQuest. So we compare the results of AlmaQuest in a similar way. And you see that in AlmaQuest, we are observing a correlation, while in the other study, they didn't. And so we think that the large scatter they observe is probably due to the sample selection effect. Then we ask ourselves, we have the empirical correlation. We can use the empirical correlation to predict the sigma molecular gas from the Balmer decrement. So is that really possible? In order to do that, we used the Karma Edge Khalifa survey. And basically what we did was to use the Balmer decrement and the AlmaQuest relation in order to estimate the sigma gas in Edge Khalifa and test if is it correct or not. Before to do that, of course, we apply the same sample selection as we did for AlmaQuest, and we check if there is a correlation between Balmer decrement and the sigma gas in Edge Khalifa, and the correlation is there. And so we test the AlmaQuest relation. Basically, you can see that we quantify the sigma gas predicted from the Balmer decrement plus the AlmaQuest relation, and we compare that with the sigma gas obtained directly from the observed CO. And you see that we found a clear relation. So we are able to predict the CO intensity on a kiloparsec scale using our relation. We also test if such relation is true and can be used in order to estimate other empirical physical relation. In particular, here I'm showing an example in order to see if we can study the Kennigat-Smith relation using the predicted sigma gas from Balmer decrement. As you can see, the result is yes, we can, because we compare the Edge Khalifa sigma gas from observed CO in red, and we compare that with what we expect from the Balmer decrement, and you see we have a similar relation with a little bit of more scatter, of course. This is my summary. So I show you that using optical spectroscopy and millimeter spectroscopy of local galaxies, we are able to identify empirical relation of the cold gas from CO emission and dust extinction from the Balmer decrement on kiloparsec scale. There is a variation with the gas phase metallicity that we need to understand. So if we need to understand if there is a connection between the dust to gas ratio or the alpha CO variation. There are strong differences with the previous works we think are due to the sample selection effect. And finally, I show you that we can use the Balmer decrement as a cold gas tracer in the absence of direct millimeter or sub-millimeter observations. And of course, I think the application in the future are kind of straightforward because, of course, with the SKA, we can extend such relation by putting the H1 into the relation. And with the NGVLA, we can, of course, study such relation at higher redshift. And that's it. Thank you.
Thank you very much. Is there any question? Okay,
Thank you for the talk. I was curious because clearly this relation is going to depend, or how scattered this relation is, will depend a lot on the spatial scale that you're examining, no? Because, I mean, you know that the extinction that you get from the ratio of the H beta to H alpha is just a measurement toward, you know, somewhere along the line of sight where you have the sources that are illuminating the material in front. The other one is throughout the entire thing, no? The entire column. So do you see that in your measurements? If you try to do things at different spatial scales, do you?
So I didn't try to push results on different spatial scale. I think that will be super cool to do that with the FANCS data because we have, I mean, very good spatial resolution, and so we can increase the spatial scale with that and see what happens. But what I did, I think I have a slide, is the fact that we start to analyze the relation, the variation of the relation according to the different distribution of the dust and the molecular gas. Of course, there are several configurations. We know that several configurations will end up with different relation, even theoretically. And now we are studying how it is applied on the AlmaQuest data. So yeah.
Thank you.
Is there any other question?
So you mentioned H1 at the very end. Presumably this shows up as extinction without associated molecular gas tracers in your observations. Do you see evidence for this?
I don't have H1 on my data.
Do you see Balmer decrement without associated CO that would indicate that there's another gas phase providing extinction?
So I'm not sure about that because of I think the spatial scale of my sample. I'm not sure about that. I mean, we can check, but I'm really curious to see, and actually to analyze a sample of data where we have H1, CO, and the Balmer decrement in order to understand the connection with the H1. Because in my data, what I observed is that in the external part of galaxies where we expect the H1 to contribute more, there is a bending on the relation. So maybe it's where we need to use the H1.
Okay, let's thank Alicia again. Okay, sorry, we have to wait for the slide to be up. Okay, so the next talk will be given by Devosmita Pathak, and she'll talk about the distribution impact of mid-infrared emission in nearby galaxies.
Great. Hello, everyone. Thank you so much for being here today. I'm Deb, or Devosmita Pathak. I'm a grad student at The Ohio State University, and I'm privileged to be giving this talk today, highlighting some of our key results from a recent publication on the distribution and impact of mid-infrared emission in the disks of nearby star-forming galaxies. So the mid-infrared primarily traces emission from small dust grains that are heated by starlight. Thanks to Adam and Karen for giving a great introduction to my talk already. And so let's dive straight into some of the key physics necessary to unpack some of the results I'll be sharing. So as stars emit in the UV and optical, especially young massive stars, these UV and optical photons encounter dust and gas in the surrounding ISM, and these interactions result in some momentum transfer and some associated direct radiation pressure. These excited dust grains then emit this radiation away at longer wavelengths in the infrared, and particularly in the mid-IR, this is through processes such as stochastic heating and thermal emission from small grains. And these IR photons can once again interact with dust grains and do another level of momentum transfer and an associated reprocessed radiation pressure. And so the emission that we see in the mid-infrared scales with both the amount of dust and gas along the line of sight, as well as the strength of the radiation field that is heating this dust. And we can use this radiation in the mid-infrared to assess the push on the dusty ISM from ionizing photons and short wavelength radiation, as well as IR photons, as we'll introduce later. So for an overview in this talk for nearby galaxies, we provide a new set of best constraints on the distribution of mid-infrared dust emission from galactic disks. We do so by constructing probability distribution functions, or PDFs, of intensity. We also talk about PDFs of gas column density, estimated from PDFs of mid-IR intensities using empirical correlations that Karen and Adam have highlighted in the past. And these are both results that have been published already. So you're welcome to scan the QR code and take a closer look. And finally, some ongoing work on some of the first estimates of infrared reprocessed and UV direct radiation pressure in star-forming regions across nearby galaxies. The data we use is from the FANG sample. So this is 19 nearby star-forming spiral galaxies at pretty high spatial resolution, 10 to 100 parsecs. The data is truly multi-wavelength in nature, and we use data from 4 MIRI filters that trace a combination of pH emission, small dust grain emission, as well as mid-IR continuum emission and some silicate absorption at 10 micron. We also combine this with optical data from VOT Muse, which is IFU spectroscopy, which captures H-alpha emission from ionized gas, as well as Balmer decrement extinction. And finally, we use higher resolution HST imaging, which also traces ionized gas. So the way we construct these probability distribution functions, or PDFs of intensity, are by binning the entire image in intensity space with some normalization. And these PDFs, although simple at face value, actually capture a tremendous amount of physics. The PDFs are expected to capture a convolution of a few different things. There's heating from small dust grains, there's turbulence in the diffuse ISM, as well as radiation pressure in young star-forming regions. And these PDFs are really cool because they're a key point of comparison between simulations and observations, as well as across different observations within the local group and beyond. And so diving straight into what some of our results look like, here is what the PDFs of galaxies look like. This is NGC 4321. Across all 4 wavelengths, the PDFs have some structure to them. There's a key contribution from the disk, which appears as a log normal peak at lower intensities, plus some structure associated with the centers at higher intensities. And you can see that the centers show some variation with wavelength. And indeed, across our full sample, the centers are kind of doing their own thing compared to the disks. And so we block out the centers, and we only look at the disks for this analysis. And once we remove the centers, a very consistent picture emerges. The probability distribution functions of the disks of these galaxies look very consistent, indeed across our full sample and across all 4 filters. There's a consistent log normal plus a power law shape. And once we use H-alpha masks, H2 region masks from VOT Muse, we actually see that the log normal component is essentially capturing emission outside of young star-forming regions, outside of H2 regions. And then the power law is actually built up by adding up contributions from young star-forming regions. And this power law component that traces star formation is actually much more prominent at 21 microns, which is a better tracer of the small dust grain continuum and hence a better tracer of the radiation field strength. And so we characterize these PDFs across our full sample of 19 galaxies and 4 wavelengths in the mid-IR. And we see that the power law slope, again, is much shallower at 21 microns. So the power law component is much more prominent and captures more of the flux, of the total flux in the mid-IR. The log normal median intensity shows systemic variation with wavelength, which is consistent with 7.7 and 11.3 microns being right on top of 2 really strong high emission features, and then 10 and 21, which typically show depressed emission. And then the log normal width shows quite little variation across our full sample, despite capturing a lot of diversity in morphologies. And we also see that this PDF, this 2-component picture of the PDF, actually only emerges at very high resolution, at sub-arc second resolution. So these are resolutions where we can actually resolve individual star-forming regions out from the diffuse ISM surrounding them. So from right to left, from lower to higher resolution, you can actually see that the 2-component PDF is only visible at high resolution. Using these PDFs of mid-IR intensities and strong empirical correlations between 7.7 micron emission in the mid-IR and CO 2-to-1 intensities. We also compute really high resolution gas column density PDFs at about 0.3 arcsecond resolution. And these PDFs look surprisingly log normal and pretty consistent across our full sample of galactic disks. And we get typical CNM projected gas column densities. And the widths of these PDFs actually translate to Mach numbers of isothermal turbulence. And we get Mach numbers of order 5 to 10. So these are driven by supersonic isothermal turbulence. And now turning to the star forming regions or the H2 regions, the 21 micron power law in the mid-IR is actually correlated with the H2 region luminosity function in the optical. And we find typical 21 micron intensities in H2 regions of order 10 megajanskis per steradian, which translates to about 250 solar luminosities per square parsecs. This means that most of our H2 regions lie comfortably below the Eddington limit, while some regions in the centers actually approach their Eddington luminosities. And radiation pressure is an important feedback mechanism in these H2 regions. And so this is some ongoing work that should hit the archive in the next couple of weeks, where we look at radiation pressure, both UV direct as well as infrared reprocessed components across 20,000 H2 regions in nearby galaxies. And so there are a lot of considerations and a lot of physics that goes into making any of these measurements, which I'm happy to talk about later during the Q&A or one-on-one. But first, we need to understand what light is emitted originally by the central powering source. And for this, we need to understand what the powering source is. And we use Starburst 99 simple stellar population models for this purpose. Next, we need to understand what fraction of the emitted light at each wavelength is captured by dust. And for this, we use the Hensley and Drain 2023, the latest astrodust models, as well as the Gordon 23 extinction curves. And finally, what light escapes. And this is where the fun stuff is. This is where our observables are. So we have optical H-alpha emission from MUSE as well as HST. We also have the Balmer decrement attenuation from MUSE. We have mid-IR dust emission for the very first time at very high resolution from JWST MIRI. And finally, we have our best estimate of H2 region sizes from high resolution HST H-alpha imaging. And combining all of these things together, we present one of the first direct estimates of infrared reprocessed versus UV direct radiation pressure for a large sample of H2 regions outside of the local group. Our Banks points are in red, blue, and yellow, split up by local environment for each galaxy. And we see that we're spanning a new parameter space, which is actually quite consistent with the LMC and SMC pressure estimates from Lopez 2014. We find that the reprocessed radiation pressure is of order 10% of the direct radiation pressure. Reprocessed radiation pressure can actually exceed direct radiation pressure on small scales and in extreme environments, such as galaxy centers, as you can see from the orange contours. And finally, the p-ion, which is the pressure from ionizing photons, which ionize hydrogen in the surrounding ISM, dominates over the direct radiation pressure on dust grains, only in relatively dust-free regions. And so in conclusion, we find a roughly log normal plus a power law PDF of mid-IR intensity for all 19 star-forming galaxies across 4 different mid-IR wavelengths, which is very consistent across our full sample. We also construct very high resolution 0.3 arcsecond gas column density PDFs for the first time outside of the local group. And we find that the gas on average is driven by supersonic turbulence. And finally, we also produce a new estimate of the total IR reprocessed radiation pressure in more than 20,000 H2 regions across nearby galaxies. And we find that the IR component is on average of order 10% of the direct radiation pressure. So thank you, and I'll take any questions now.
Thank you very much. Any question?
Thanks. Really interesting talk. I was just wondering with 1512 you showed earlier, but you're not continuing with it. I mean, in the analysis, it's got quite an interesting prominent bulge. And just 1512. I think you showed it earlier, and I was sort of trying to look in there.
I'm not sure I included 1512. Are you talking about?
Yeah, I was.
this
So
galaxy?
I'm not seeing it in your further analysis, but I think you did show it earlier. I was wondering what's happening with the really prominent bulge, and then the very empty regions around that.
Yeah.
You perhaps have an idea?
Yeah, a lot of our galaxies, I think 16 out of the 19 galaxies in my FANG sample are actually barred. And the bars do show up. They're major contributors to that power law component, since the bars actually have a tremendous amount of star formation going on, and most of them are lit up in H alpha, so they're within H2 regions as well. So the bars actually are a crucial component of that power law in the PDFs.
All right, thanks. Yeah. Thanks.
So I'm sorry, we have to move on. So let's thank Deb again. So next talk will be given by Michael Romano, and he'll talk about new evidence for outflow-induced gas and dust enrichment in the surroundings of dwarf galaxies. So please go ahead.
Sorry for this. And I also clearly mistake the size of my slides, but anyway. So good afternoon, everyone. I'm Michael Romano, and I'm a postdoc at the National Center for Nuclear Research in Warsaw. I want to thank the organizers for giving me the opportunity to present our new recent results on the effect of galactic outflows on the evolution of dwarf galaxies, and in particular on their gas and dust distribution around them. So let me start with a very schematic representation of the life cycle of a typical star-forming galaxy. Here you can see in the background an image of composite image of MET2, where in blue there is the stellar emission, while in red you can see the H alpha emission coming out perpendicularly from the stellar disk in this very huge outflow of ionized gas. However, if you want to describe the evolution of this galaxy across cosmic time, then we have to account for some key ingredients of the so-called baryon cycle, which is the set of complex phenomena ruling the interplay between gas, dust, and star formation within the galaxy. So we can say that at the beginning of this cycle, the gas can cool down to allow the formation of new stars, which in turn evolve, giving rise to stellar winds and supernovae, and enriching the interstellar medium with heavy elements and dust. And both star formation and AGN can produce very strong winds in the galaxy, exerting a feedback in their ISM, producing possibly stopping the formation of new stars by pushing the interstellar medium material outside of the galaxy. And depending on the outflow velocity, this material can stay bound to the stellar disk or brought outside into the CGN, where it can still be reused for future star formation, but it can also leave completely the galaxy, enriching the intergalactic medium. And apart from this, we can also have other external processes, like, for example, the inflow of gas from the cosmic web, or the presence of faint satellites or mergers can contribute to the baryon cycle as well. However, during this talk, I will focus specifically on the effect of galactic outflows on the gas and dust distribution around galaxies. So there are now many more observations of, especially in the high Z universe with ALMA, of star-forming galaxies characterized by extended gas reservoirs and also dust which extend actually up to several kiloparsec from the stellar disk. However, although at this redshift we do not have enough resolution to distinguish between the mechanisms at the origin of this extended emission, there are still many observational works, but also cosmological simulations and semi-analytical models suggesting that outflows can actually be possible drivers of this kind of extended emission in these galaxies. And this is the reason why we decided to investigate the effect of outflows more in detail in the local universe in star-forming galaxies, specifically in the dwarf galaxies. Indeed, dwarf galaxies are much more sensitive to feedback with respect to higher mass galaxies because of their shallower gravitational potential. And in the local universe, they can offer a unique opportunity to study outflow in great detail. Also, dwarf galaxies are thought to be analogs of high-Z sources because they share similar properties in terms of star formation efficiency, size, and metallicity. And these offer the chance to provide some constraints on the baryon cycle of their counterpart in the primordial universe. So because of this, we selected a sample of dwarf galaxies from the Dwarf Galaxy Survey. This is a collection of 48 dwarf galaxies with distances smaller than 200 megaparsec and subsolar metallicity. You can see here the galaxies as observed in the far-infrared by Herschel. And we took advantage of the single ionized carbon line, the C2 at 158 micron, in order to see the effect of galactic feedback in these galaxies. We chose this line because this is one of the major coolant of the ISM. It is one of the brightest line in the far-infrared regime. And it is also a good tracer of the atomic gas. And it was already being used in previous studies to spot galactic outflows both in the local and IZ universe. So we selected a subsample of 29 galaxies from the parent DGS sample in order for these galaxies to be completely covered by the PAC spectrograph on board of Herschel that observed the C2 line and having a good signal to noise in C2. As you can see, our targets lie along the main sequence of star-forming galaxies. They are characterized by stellar masses between 10 to the 5, 10 to the 10 solar masses, and star formation rate from 10 to the -3 to 10 solar masses per year. All of these galaxies show signatures of outflowing gas as traced by the C2 line, in particular by looking at the broad component at high velocities, which is a signature of outflowing gas. And we also found that all the outflow in these galaxies have velocities larger or comparable to the escape velocities of the galaxies, suggesting that a lot of gas can actually be pushed outside the galaxy into the CGM. I will not say more about this, but if you want to know more about outflow detection in these galaxies, please come on Friday to see my talk in Division H. So we first excluded all the possible mergers or disturb morphologies in these galaxies. And we selected subsample in the UV, far-infrared, and C2 emission in order to see the diffuse emission both in the dust and in the gas, and in the stellar emission as well. So we used GALEX and Herschel observations for this. And here you can see the stacked images in the UV, far-infrared, and C2. We extracted yes. So for each of these images, we extracted the corresponding radial profile. And as you can see from these, as you can see from these images, the gas and dust resulted to be more extended than the UV continuum in these galaxies. And in order to be more quantitative on this, we also model the light profile with Sersic functions. Here you can see that actually in order to reproduce these profiles, we needed a double Sersic function, including both a narrow and broad component. And the broad component was actually more important for the far-infrared and the C2 emission with respect to the UV emission. And this broad component was needed in order to reproduce the profile, especially at the largest radii. So we also compared our results with other observations of high Z star-forming galaxies as observed with ALMA, for which there is evidence of extended C2 and dust emission that is attributed to the presence of outflows. And as you can see, both for the gas and the dust, our results are similar, are comparable with the effective radii of these star-forming galaxies, suggesting that there can be some common origin of the mechanisms producing this kind of extended gas and dust reservoir in their CGM. However, at IZ, the situation may be much more complicated. As I said before, we do not have enough resolution and sensitivity to really understand what are the mechanisms at the origin of this extended emission that, apart from outflows, can also be attributed to the presence of faint satellites, but also to the gas stripped during merging events. So for sure, more analyses are needed, especially at IZ, to understand what's going on in these galaxies. And finally, regarding this, for coming facilities like, for instance, NGVLA, but also SKA, but also on telescope under design like Atlas, will actually allow us to solve this issue, especially in the high redshift universe, by tracing the faint and hidden CGM and IGN emission around galaxies. And in particular, with these facilities, we will be able to link the emission from the CGM with the physical processes happening at the sub-kiloparsec scale in these galaxies. And also, they will allow us to trace the very faint H1 emission from dwarf galaxies up to very high redshift, and also other tracer of the gas like low JCO transitions from very high Z galaxies. So this will be a very important discovery, let's say. And with this, I will leave you the conclusions, and I'm happy to take any questions. So thank you.
Thank you very much. Any question?
Regarding your first point, for nearby dwarf galaxies, we have spatially resolved H1 and H alpha data and even CO data from ARMA now. And there is no such evidence of widespread outflows. I mean, when we see gas deviating from rotation, typically have low velocities, so they're more like galactic fountains. So can you comment on this? Why C+ that in principle trace a combination of H1, CO, and H alpha should give a different result?
Yeah, first of all, you can come on Friday. I will talk about this for sure. But yes, we found evidence for C2 outflows in these galaxies. The starting point was actually to understand if these dwarf galaxies were showing this kind of outflow gas in C2. We have also some observation of H1 from VLA and also ATCA for these galaxies in particular. They also show extended H1 emission as expected. In terms of C2, I don't think it's so unusual to find some kind of outflows because C2 can trace, as you said, different phases of the ISM. So in this case, we think this is tracing mostly the atomic gas. And there are evidence also at IZ that there are outflow in C2. So maybe I didn't get the question.
Maybe my question wasn't clear. I was saying that in dwarf galaxies, when we trace H1 in emission in a spatially resolved fashion, in most of the cases, H1 is rotating with no evidence for outflows. So it's a bit suspicious that you see outflows in C+ in unresolved data when the same tracer spatially resolved doesn't show them.
But it's also true that spatially resolved data in some way miss a bit the sensitivity for tracing the outflow. We can chat later about this.
I have a related question regarding the outflows. Are you using just a double decomposition method in order to identify outflows? Because we already know that even if we don't have an outflow, we have a normal galaxy that is rotating, the global emission, the shape of the global emission is not a Gaussian, a narrow Gaussian
Yeah,
line.
but we found broad component at velocities of 500 kilometers per second.
But your spectral resolution is very low.
It's 230 kilometers per second for Herschel, yes. But
yes.
we accounted for spectral resolution. We subtracted this from the Gaussian decomposition, of course.
Yeah, I mean,
how do you explain this kind of very high velocities, broad components?
I don't know, maybe you can try to model in a more sophisticated way the galaxies, I don't know. And
Yeah,
then
for
you
sure,
see
but
if
this
at
is not
such a resolution you can identify or not the outflows.
Yeah, no, of course. It's something that can be done, but for sure, right now, I don't know how to explain this kind of very high broad components, high velocity broad component in other terms. Of course, we can apply other methods, but this is just a method that is applied usually in the literature. So
We can discuss later, but
Yeah,
maybe
yeah,
it's
yeah,
just a
sure.
combination of very low spectral resolution and the fact that the galaxy, I don't know, it's interacting or maybe it's just rotating, but we can
for
discuss later.
interactions, no, because we excluded, but yes, we can discuss.
Okay, so we have to move on. So let's thank Michael again. So the next talk will be given by Nicholas Pingel, and he'll talk about revealing the role of atomic hydrogen in molecular cloud formation. So please go ahead.
Okay, thank you. I realize that I'm the last thing standing between everyone and their food at the end of the day, so I'll try to be as succinct as possible. The two beautiful images that I'm showing here are peak H1 maps of two local group dwarf galaxies, NGC 6822 and the Small Magellanic Cloud. And these respectively come from two active wide field H1 surveys, the local group L-band survey done with the VLA on the left, and GasCap H1, which was talked about a couple times today, performed with ASCAP. And the low metallicity of these galaxies provides gateways into probing the structure of the gas on tens of parsec scales to characterize the heating and cooling mechanisms that were active in early universe-like conditions. So the pressure versus density diagram on the left, I'm showing this black, here we go. This black curve is the thermal equilibrium curve. And these are taken from simulations. And I think it nicely summarizes the unique multi-phase nature of H1. So at low densities, you have the warm neutral medium phase. At high densities, you have a cold neutral medium phase. And in between these two gray horizontal bands, we have a range of interest of thermal pressures where these two phases of the ISM can coexist. And you also have a third phase, the lukewarm neutral medium or unstable neutral medium that comes about in part due to turbulence. And we can see that if you vary the UV background, that's what's denoted by these blue and red dash curves, we see that the thermal equilibrium will shift. And this is this shows that it's vital to trace the properties of the CNM over a variety of astrophysical environments if we ever want to have a chance to understand the role of the CNM as it shields molecular gas from photoionization, and also how it sets locally the star formation rate and star formation efficiency, because these are currently unconstrained observational. But due to the inherent low spin temperatures of the CNM, most of the observed H1 that we see in emission arises strictly from the W and M phase. And so what we have to do to unambiguously trace the CNM, as Naomi spoke about earlier this afternoon, is trace it through absorption. And by tracing it in emission and absorption in conjunction with one another, we can estimate important properties of the CNM, such as the spin temperature. At the densities of the CNM, the measuring of the spin temperature, it is basically a proxy for the kinetic temperature. So this allows us to relate back to numerical simulations of the multi-phase ISM. So thus, while we can measure the spin temperature, we need to get this ratio of emission to absorption on parsec scales with these surveys. We are limited to pencil beam measurements to wherever there's a suitably strong background source. So the CNM has been detected in absorption over a wide range of redshifts. So for example, this is taken from a galaxy-wide CNM properties from the flash survey that's done with ASCAP. But at these redshifts, the H1 emission that you need to get something like the spin temperature is too faint to observe. So you must make some sort of assumption about the emission properties to be able to say something about, like, say, for example, the spin temperatures. More closer to home, we have surveys such as 21 Sponge and the Hylas and Trollin work that was done in the early 2000s to say important things about the CNM properties within our own Milky Way. But a lot of these surveys are restricted to high galactic latitude sightlines. To a lot of high galactic latitude sightlines because the emission and absorption profiles get quite complicated when you look through the plane of the galaxy. Other surveys of the Magellanic Clouds do a bit better because you don't have to deal with the galactic plane. And this is a good way to probe low metallicity environments in the Small Magellanic Cloud and SMC. However, sensitivity constraints have limited H1 absorption detections strictly to the Magellanic Clouds with only a handful of low resolution detections in M31 and M33, and that is until now. So really we've been kind of limiting our understanding of how the CNM properties vary in different astrophysical environments that are afforded by other local group member galaxies. So the two surveys I'm going to focus on today are summarized in these plots. On the left, I'm showing the galactic ASCAP H1. This is galactic ASCAP survey. I'm showing the full survey coverage, or at least I thought I was going to, but some of those panels are not showing up, but Naomi showed it earlier today. But basically, we use the 25 square degree field of view of ASCAP to obtain an order of magnitude increase in sensitivity from previous surveys, which enables us to create truly unprecedented H1 data sets of the Milky Way and nearby Magellanic System. And due to their proximity, they are the perfect laboratories to study H1 emission and absorption in conjunction with one another in order to study the phase changes. And just to summarize quickly, we'll have 200 hours of integration on the Magellanic Clouds and 50 hours of integration along the Magellanic Stream, and also a strip along the galactic plane and galactic center. Now, on the right, I'm showing an example data set from the local group L-band survey, or LGLBS. This is an extra large project with a very large array, and this includes all configurations of the VLA, so including the A configuration. So we get these 27-kilometer baselines so that we can actually probe down to the same physical scales, tens of parsec scales, that we can in GasCap H1. Basically, we're extending our high-resolution view of the Magellanic System and Milky Way to several prominent members of the local group. So these are summarizing some of the results from GasCap H1, specifically the absorption. While you've seen some examples of some excellent H1 emission maps from GasCap, really the workhorse scientifically that's been done in the early stages of the survey has been done with the H1 absorption. So here I'm showing on the left results from James Dempsey's work, who's a PhD student at ANU. So he expanded the sample of sightlines around and through the SMC from a staggering number of 229 total sightlines, and 62% of those sightlines contained within the SMC have reliable CNM detections. Interestingly, and I think Naomi also talked about this, you see about 11% of those sightlines that lie outside of the main body of the SMC. You can see, I keep hitting not the laser, there you go. You can see that these are detected where there's little to no H1 emission, and at velocities, the components of the absorption are at velocities that are not moving with the bulk velocity of the Magellanic, of the SMC. And also the CNM mass fraction was about 11% over the total sample, so this is quite low, but it's not too surprising because the metallicity is quite low and that's stifling cooling in the ISM. On the right, we have a result from a single field that was centered on a galactic longitude of 340 degrees. And this is work that was led by John Dickey. And basically, we're seeing the ratio of the emission in orange to the absorption to get a measurement of the mean spin temperature. And then we see that the mean spin temperature, this ratio stays constant out to kinematic distances that correspond to about 40 kiloparsecs. So this is really changing our view of how we view the cold neutral medium distribution within our own galaxy. So to extend now out to the local group, this is a paper I recently published showing the two first localized H1 absorption detections in a low metallicity environment that's outside of the Magellanic Clouds. This is in the dwarf galaxy NGC 6822, which is a similar metallicity to the SMC. And through a Gaussian decomposition that was led by Hongjing Chen, who is a PhD student at UW-Madison, we were able to show that several components of these absorption detections have mass fractions of about 0.2 to 0.3 and a mean spin temperature of 36 Kelvin. And interestingly, this northern detection actually intersects a region of active star formation. And poking around that region, we have the H1 absorption in the cyan, and then intercepts exactly the CO, and you see that it sits in a depression in the H1 column density. And so this is not some sort of H1 depletion, it's actually coming from H1 self-absorption. And poking around, you can see different sight lines that indeed you see a very distinct HISA dip. So this is the first detection of HISA outside of the Magellanic Clouds in M31 and M33. And it implies that the CNM is not traced just by H1 absorption. We can actually see it extended if we look at the H1 self-absorption. And so future work in this direction, I think, would be to characterize the CNM through emission, whether it's going to be through H1 self-absorption. There's also some machine learning algorithms that are being developed. So give a shout out to Van Heep, look at his talk next week, Wednesday, where he's going to talk about a convolutional neural network approach to use the H1 emission profiles to pull out the absorption properties. And also, if we look at the dynamics of the H1 relative to the CO, we see an offset that Juan also talked about earlier today. So just to give a quick shout out to Ayel Stalila, who is a UW-Madison PhD student. She's doing similar work in the LGLBS sample, and we see the exact same thing where we see H1 absorption in a low metallicity environment in ISA 10, and indeed we also see instances of HISA as well. And so I think what I'm looking forward to, I think we really need to focus on the fact that HISA might be an emerging and blossoming field as we move into the SKA and NGVLA eras, because you're going to be able to map out H1 absorption, the CNM, not only through H1 absorption, but also through extended mapping of the H1 self-absorption as well. The GasCap H1 and the local group survey are pioneering these efforts in advance of these next generation facilities. And finally, I just wanted to shout out some current work that's being done in preparation for these large densities of H1 absorption that we're going to detect. We're going to be able to use H1 absorption and H1 self-absorption in conjunction with one another to map out the cold neutral medium distribution, but also we need to develop methods to do this. Currently, this is being done with a package called AstroSaver. This has been applied to the Thor H1 data along the galactic plane. And so this uses synthetic H1 data to pull out to try to find across an image all the instances of H1 self-absorption where we can actually get a map of the cold gas. So I think this is where the field is heading towards as we get into the era of the SKA and NGVLA. So finally, I will realize I was not as succinct as I wanted to be, so I'll just leave up my conclusions, but I want to just shout out that I think GasCap H1 and LGLBS, these are sister surveys, and they're going to open up a new observational regime for measuring the thermodynamics of the CNM across a wide range of astrophysical environments. So thank you, and I'm happy to take questions.
Thank you very much. Any question? So how often do you see the self-absorption?
That's a good question. So we see where we have all overlapping molecular gas data, we see instances of HISA, not as statistically significant as the ones I was showing, but we see hints of it. And so we haven't done a search where you don't have molecular gas, but I imagine if we did a close search, we would see instances of that as well.
Okay, thank you. Any other question?
Thank you for your interesting talk. And you showed H1 emission distribution of the NGC 6822. And there were two H1 observation lines. And could you go back to the slides? It looks like one H1 observation line, the square, looks like correlate with the H1 shell. So does it relate to the H1 shell, and does it shows the enhanced CNN mass fraction compared to the other one?
That's right. I believe the southern detection has the higher CNN mass fraction, but we haven't done a detailed look into its relation to the obvious shell that's there. Yeah.
Yeah, I think it's interesting target. Yes.
Okay, so it's about time. So let's thank Nicholas and all the speakers in this session.